The clean room at 0200 has the stillness of a sealed archive. Temperature fixed at 68 degrees Fahrenheit. Humidity at 30%. The air filtration cycles every 90 seconds with a soft mechanical exhale that is the closest thing to breathing the room knows how to do, and in the gap between cycles the silence is absolute. No street noise, no building vibration, no distant HVAC rattle bleeding through the copper mesh walls of the Faraday enclosure. The room absorbs everything. Outside, Worcester is asleep under low November cloud. In here there is no outside. Director Elias Thorne has been on site for 16 hours. His lab coat is creased at the elbows from leaning, and he has a ring of cold coffee on the bench that he has not cleaned because cleaning it would mean stopping, and he has no intention of stopping until the shift log is complete, and every anomaly flag from the previous night's scan has either resolved or been escalated. He runs his inspection schedule the same way he runs everything, methodically, from the baseline outward, looking for the thing that should not be there. He has been doing this for 20 years. The work makes him good at noticing. The Lunar Roving Vehicle sits on the stainless steel specimen platform at the center of the room. Platform designation, Station Alpha. Specimen designation, LRV-02. Serial number as built by Boeing Aerospace. Worcester Assembly, 1971. Property of the National Aeronautics and Space Administration. Currently on loan to the Worcester Restoration Facility under Project Ledger. The rover is approximately 3 meters long and weighs 102 kilograms in its current configuration. Under the LED arrays, it looks precisely like what it is. 55 years of storage compressed into aluminum and wire mesh wheels and a communications dish, angled 45 degrees upward toward a section of ceiling that has never once received a transmission. The gold-plated Mylar thermal blankets are crazed with age, the edges peeling in thin curled strips like sunburned skin. The seats are folded down. The handlebars wait at the exact angle a dead man last gripped them. Thorne makes a note about the Mylar degradation in the shift log. Tomorrow's first task is insulation assessment. He wants photography under UV before anything gets touched. The whole point of this project is the hardware. You do not rush the patient. Thorne runs the LiDAR array at the start of every shift. Protocol mandates once per 24 hours. He runs it twice. He uses it to confirm the patient hasn't shifted overnight. Hardware that old can move. Thermal contraction, residual outgassing, the slow settling of fatigued welds. He likes to know where things are. The LiDAR sweeps the room in a continuous 30 Hz pulse, building a point cloud wireframe of the room geometry in real time. The white walls, the platform, the specimen, clean, measurable, accountable. Numbers he can verify. The first pass returns clean geometry. He logs the dimensions and moves on. He runs the second pass at reduced sweep rate. Slower, better per-point accuracy. The mode he uses when he is looking for micro-deformation. Small things. The point cloud renders on the primary display and something in the chassis is moving. Thorne leans forward. He watches the data. The aluminum frame, the primary longitudinal chassis spar, the front axle support tubes, the instrument panel mounts, is oscillating. A rhythmic micro-tremor, small enough that a standard daily scan would smooth it into measurement noise. But he is watching in real time, and the motion is there in every frame of the render, consistent and metronomic, the frame shivering in place like a compass needle over something buried. He counts the cycles against the display timestamp. 1.2 Hz, 67 times per minute. The chassis has been doing this for at least the 11 minutes the scan has been running. He runs the environmental cross-check first, because he is methodical and because he already knows what the results will say. The building's pneumatic isolation mounts are rated to filter all structural vibration below 20 Hz. The HVAC runs at 60 Hz, and the Faraday enclosure damps it by a factor of 1,000. He checks the seismic monitor. There is no seismic event in progress within 700 kilometers. He checks the acoustic monitor. No external sound source above threshold. He checks the platform temperature log. Stable within 0.2 of a degree for the past 6 hours. No thermal expansion, No vibrational coupling from the building. No instrument artifact. The chassis is oscillating. The chassis should be still. The chassis has no power source. He does not reach for the phone. He picks up the contact microphone from the bench and crosses the room. The clean room has no windows. The walls are white-painted steel panels over copper mesh, sealed at the seams with conductive tape. The floor is polished epoxy, anti-static, trace-heated from beneath. At 2 meters from the specimen platform, Thorne stops. His forearms register at first. A subtle pressure differential in the air column. The sensation you get standing close to a speaker cone when no signal is playing. Not a temperature change. The room sensors confirm 68 degrees to within a tenth. Something else. The physical presence of subsonic vibration moving through the air. He notes it in the back of his mind where he stores things he doesn't have words for yet, and keeps moving. He clips the contact mic to the main chassis spar and runs the lead back to the audio analyzer. He fits the headphones. The sound enters him like a key finding a lock. Low, smooth, periodic, not mechanical. No harmonic complexity, no jitter of a loose fastener, no resonance of a vibrating panel. This is clean. A metronomic thrumming that registers in the chest before it registers in the ears, the way a cathedral organ sits in the ribs before the brain catches up. It comes at steady intervals, and the intervals are precise, and Thorne counts them against the second hand of his watch. 72 beats per minute. He knows what 72 beats per minute sounds like. He has heard it in hospitals, in field medic stations, clipped to his own finger. He removes the headphones. He sets them down with care. He walks to the south wall, to the circuit breaker panel marked Facility Main in black stencil, and he throws every breaker. The LEDs die. The air filtration winds down through its operating frequency in a slow descending chord and goes silent. Every instrument on every bench cycles down and goes dark. The room fills with the specific quality of darkness that exists only in sealed windowless spaces. 3 seconds of fading phosphorescent glow from the dead LEDs, and then nothing. Total black. Total silence. Thorne stands still. He listens. Through the polished epoxy, through the soles of his shoes, through the dead air of a room with no running instruments and no power source of any kind, the rover is still moving. The vibration is in the floor. It is in the copper mesh of the walls, conducting the oscillation through the Faraday shielding the way a tuning fork spreads through a tabletop. 1.2 hertz. He counts 12 full cycles in the dark, each one precisely spaced, each one exactly the same. He restores facility power. At the spectrum analyzer, active probe against the chassis. Full band sweep from the contact point. The display builds. The 1.2 hertz fundamental appears first, clean, sharp, well-resolved, no ambiguity. The harmonic series follows it upward. 2.4, 4.8, 9.6 hertz. Perfect octave intervals, geometric and deliberate. This is not the broadband smear of random vibration. Random vibration produces noise. This produces structure. He runs the current sensor. The probe touches the main power bus. The reading renders 0 milliamps. He checks the probe, verifies calibration against the reference resistor, confirms the lead connections, runs it again, 0. A third time, 0. No current in the wires. No electrons moving through any conductor in the system. But the spectrum analyzer, attached to the same chassis, reading the same bus bar, is registering an active, structured, harmonically organized signal sourced from this hardware. He goes through the list in his head the way he always goes through the list. Stray inductance from the building's own electrical infrastructure, ruled out. The Faraday enclosure eliminates inductive coupling. Seismic micro-vibration from the building structure, ruled out. The platform sits on pneumatic isolation mounts, rated to block frequencies below 20 Hz. Capacitive artifact in the analyzer itself, ruled out. The reference channel is clean. Calibration error, ruled out. 3 independent passes. The air filtration exhales. The cycle resets. The room breathes. There is no explanation on the list. There's only a dead machine producing a living signal through wires that carry nothing. He keys the intercom. "Sully, wake up." A pause. The sound of something being knocked sideways. Then her channel opens. She is already live, already tracking. "I'm awake. I've been awake. What did you pull? Get in here." She arrives in 4 minutes, which means she was already dressed, which means she heard the facility power cycle and knew before he called. She carries a stimulant can in one hand and her probe kit in the other, and she goes directly to the analyzer display without being told. She stands very still for a long moment, which is not her default. Sully's default is in motion. And then she pulls her own probes from the kit and runs an independent verification on a separate analyzer channel, muttering under her breath the whole time. The fast, low-register narration she uses when the data is running faster than her words. Fundamentals on the floor. Right on it, 1.2, clean return, not noise. Harmonics are stacking perfectly, 2-4, 4-8, 9-6. This is sourced. It's not environmental. The return signature is coming from the chassis, from the spar. She stops. She looks at the current readout. Both of those can't be right. 3 current readings, independent probes. But the signal has structure. She is already moving to the header analysis. It's got harmonics. It's not bouncing off the walls. The return is clean. Elias. She goes still. The signal has a header. "Tell me." "It's a 2026 encryption standard." Her voice has lost the speed. Flat, careful, the register she uses when she needs to be precise. AES variant. NIST proposal that hasn't cleared committee review. We haven't published it. We haven't even circulated the draft publicly. She looks at the rover. This hardware was built in 1971. I know. A not yet published 2026 spec header from a 1971 chassis, drawing 0 current through the wires. She sets the headphones down on the bench and doesn't pick up her stimulant can. Who built this? Thorne looks at the rover. 20 years of dead machines. He knows what dead looks like, the texture of it, the way hardware that has truly stopped announces its stillness in a dozen small physical tells. Brittle insulation, surface corrosion at every terminal, the subtle forward slump of a structure that has not borne its own weight under gravity for half a century. The LRV-002 has all of it, and beneath all of it, a pulse, structured, encrypted, addressed. He says it flat, the way he says things he needs on record. The batteries were pulled in 72. The capacitors are dust, but this chassis is drawing 5 watts from nowhere. Sully doesn't answer. The spectrum analyzer marks the next 1.2 Hz cycle, then the next, then the next. The air filtration exhales. 90-second cycle. The room breathes. He picks up the marker and writes on the whiteboard above the station. 0 current. Active signal. Source. Unknown. He draws a line under it. He has resolved 219 hardware anomalies in this facility. Every impossible reading has traced back to a physical cause. Stray inductance, capacitive coupling from adjacent equipment, EMF leakage from the building's own electrical infrastructure. Bad grounds. There is always a physical cause, and finding it is always the same process. Eliminate, narrow, confirm. He is good at it. He has been good at it for a long time. He runs the process in his head now. Inductive coupling. Ruled out. The Faraday enclosure blocks inductive sources, and the facility's main wiring is 30 meters away behind 2 shielded walls. Capacitive artifact in the analyzer. Ruled out. He has 3 independent readings on 2 separate instruments, all showing 0. Residual charge in the chassis itself. Ruled out. The rover has been in storage for 55 years, and any charge distributed across the aluminum frame would have dissipated to ground within hours of delivery. He has been thorough. He is always thorough. He looks at the whiteboard. He has nothing. Sully is at her monitor bank, pulling the full header decode and running it against every known encryption standard in the facility's reference library. Her fingers move in short, fast bursts. She glances back at the rover once, the way you glance at something in a room when you are not certain whether it is looking at you back. and returns to her screen without comment. The pulse ticks on, 1.2 Hz, one oscillation every 0.8 of a second. It has been ticking at this rate since at least the moment the LiDAR array detected the tremor, and the LiDAR array has been running for 6 hours, and Thorne has no way to determine how long before that the pulse was active. He does the math. The rover was delivered to this facility 31 days ago. If the signal was active on delivery, it has been transmitting for 744 hours inside this Faraday enclosure. If the signal was active before delivery, if it was active in the transit case, in the storage warehouse, in the NASA facility where it spent the last 55 years, then the signal is older than the Faraday enclosure, older than the facility, older than everyone in this room. If it was active when the rover was sealed in storage after the Apollo program ended, the signal has been transmitting since 1972. He has not let himself say the next part yet. He says it now, quietly, to nobody. It was transmitting before that. It was transmitting on the moon. The room is very still. The filtered air moves in its 90-second cycle. Somewhere inside the sealed aluminum frame of a 55-year-old relic, something is producing structured energy from a source that doesn't exist, encoding it in a standard that won't exist publicly for another 6 months, and transmitting it through wires that carry zero current toward a destination that the header implies is deliberate and specific. When Thorne attached his current sensor probe to the chassis at 0217, the impedance of the circuit changed. The probe created a load, a measurable resistance in the bus. A live terminal knows when it has been touched. The probe's presence would have registered as a signal event at the receiving end of this transmission. He didn't initiate contact. He answered the phone. Somewhere on the other end, something has been waiting for 55 years for someone on this end to pick up. Tomorrow, Thorne pulls the Mylar. He already knows the insulation is not protecting the rover from the environment. The Faraday enclosure proved that. The signal got stronger inside the cage. The Mylar is protecting something else, keeping something in. He has no word for what he is about to find under that gold-plated skin. The patient is not done being examined, and the patient, for the first time in 55 years, knows it. Chapter 2. Stripping the Mylar. The first panel of insulation comes off at 0640, and it is wrong before it clears the chassis. Thorne has removed Mylar thermal blankets from 11 different NASA heritage specimens over the course of his career. He knows the material: gold-plated polyimide film, vacuum-deposited aluminum on the outer face, adhesive-backed where it meets the structural substrate. After 55 years in storage, it should be brittle, micro-cracked from thermal cycling. The adhesive crystallized, the film stiffened into a shape that no longer remembers being draped around a three-dimensional object. It should crumble at the edges when the seam tape is scored. It should feel like handling a dead leaf. This panel does not feel like a dead leaf. The instrument panel section comes away in a single intact piece, supple and uncracked. The gold surface still coherent and reflective under the overhead LEDs. Thorne holds it and examines it under the magnification ring lamp. No delamination. No microfracture network. The adhesive on the inner face is still tacky. Not crystallized, not dried. Actively tacky. The way a new panel feels coming off a clean room roll. He runs a thumbnail across it and the material grips. He sets it in the specimen tray and does not say anything about it. He writes it in the log. Insulation integrity anomalous. Panel 1, adhesive active. Film undegraded. He reaches for the second panel. The clean room is running a full instrument suite this morning. Spectrum analyzer live on the 1.2 Hz pulse. Still present, still metronomic, still generating zero measurable current through any conductor. The contact mic is still clipped to the main chassis spar where he left it the previous shift, still feeding into the audio analyzer, still delivering that low rhythmic throb that the headphones translate into something that sits in the chest. Sully is at the monitor bank with fresh stimulant and no expression, running the header encryption analysis for the fourth continuous hour. She found nothing in the reference library. She ran it against every commercial, military, and academic encryption standard in the facility's database and came up empty on everything except the unpublished NIST proposal, which she has now pulled in full technical draft from her secure academic access and is attempting to reverse match against the signal's header structure. "Still nothing on the header source," she says, not looking up. The NIST draft matches the architecture, but the implementation in this signal is cleaner than the draft. Like whoever wrote this signal had a finalized spec. Or wrote the spec. She doesn't answer that. The second panel comes off. Same condition as the first. Pristine, supple, adhesive, active. Third panel. Fourth. Every section of thermal insulation on the LRV-002 is in new manufacture condition, and Thorn adds each anomaly to the log in the same flat notation, and by the time he reaches the primary bus bar housing, the log entry is 12 lines long, and all 12 lines say a version of the same thing. This hardware did not age. He sets the final Mylar section in the tray and looks at what is underneath. The main power bus runs along the central longitudinal spar, a thick bundle of copper conductors, insulated in the original Boeing specification PVC jacketing, routed from the now absent battery tray at the rear of the chassis forward to the telemetry relay housing at the front. The wiring is original NASA build, 55 years old, and it should look exactly like 55-year-old wiring. Oxidized copper at any exposed terminal. PVC jacket yellowed and beginning to harden. The kind of wiring you handle with cotton gloves and still hold your breath. There is something wrong with the bus bar housing. Thorn leans in under the magnification lamp and sees it clearly. A coating. Thin, conformal, silver-tinted, following the surface topology of every wire and terminal and connector block with absolute precision, as if it were sprayed on from 6 inches away and cured in place. Not a contamination. Too uniform, too comprehensive. No drip marks, no overlap artifacts. A deliberate application. It coats the bus bars, the terminal posts, the connector crimps, the wire bundle ties. Everywhere the original copper is exposed or nearly exposed, this material has formed a continuous film over it. He runs the UV wand over it. The coating pulses. Not a reflection artifact. Not phosphorescence from the UV source bleeding into the wand's own reading. Thorn has used UV inspection wands in clean rooms for 2 decades, and he knows every artifact that lamp produces. And what he is looking at is not an artifact. The material absorbs the ultraviolet and then emits in the blue-white range a photonic response, a material that is actively processing the input energy. And the emission is rhythmic. It brightens and dims in a regular cycle. 1.2 Hertz, 67 times per minute. The coating on the bus bars is pulsing in exact synchrony with the chassis vibration, with the signal on the spectrum analyzer, with the audio throb coming through the contact mic. The material is part of the system. It is not contamination. It is infrastructure. The air filtration exhales its 90-second cycle. In the relative quiet after it settles, Thorn becomes aware that the subsonic pressure he has been feeling in his forearms since he entered the room is slightly stronger than it was at 0200. The chassis is closer to him now, insulation removed, and the field it produces, whatever it is, whatever physics describes it, is no longer attenuated by 55 years of gold-plated polyimide film. He realizes the Mylar wasn't protecting the rover from the environment. It was muffling the signal. "Sully, document the UV response on the bus bars." She is already at his shoulder, camera running. He hears her breathing change, a brief pause, the kind you make when something on the screen does not match what your training says. Screens are allowed to show. Then she exhales and keeps filming and says nothing. He takes the wire stripper and selects a 10-centimeter section of the primary bus bundle toward the rear of the chassis. The battery side end, farthest from the active telemetry relay, minimum disruption risk. He scores the outer bundle wrap. He peels back the bundle tie and selects a single conductor. He scores the PVC jacket. He peels it back. The copper is gone. He does not move for 3 seconds. He looks at the exposed section of wire under the magnification ring lamp, and what he is looking at is a solid strand of translucent crystalline material, approximately the diameter of the original copper conductor, occupying exactly the space the copper should occupy, routed exactly the way the copper was routed. It is not copper. It is not any metal in the facility's material reference library. He knows this immediately and intuitively from the way it catches the light. a kind of deep internal refraction that copper does not produce, the light entering the strand and emerging from the far end, as if the material is a waveguide, as if it is moving something through itself. The strand is glowing, not bright. A faint luminescence, below what you would notice in a lit room if you were not looking directly at it, but unmistakable under the magnification lamp. The translucent crystal is conducting something, and the something produces light, not heat. He runs the thermal probe immediately. The strand is at ambient temperature, 68 degrees exactly, no thermal signature beyond the room baseline. Not electricity in the classical sense. The current sensor reads 0 as reliably as it has read 0 every time he has probed this chassis. Something else is moving through this conductor. Something that produces photons but not heat. Something that is not on the list of things wires are allowed to carry. That's not copper, Sully says. No. What is it? I don't know. He takes the scoring tool and scores a second wire, peels back the jacket. Same result. Translucent crystal strand, internal luminescence, ambient temperature. He scores a third, fourth. He goes methodically through every accessible conductor in the primary bus bundle, 12 wires total, and every single one of them has been replaced. The PVC jackets are original Boeing specification, 55 years old, undegraded. Inside each jacket, crystal. The jackets are original NASA hardware. Everything inside them has been substituted. He stands up between the third and fourth wire and rolls his shoulders because there is a tightness in his upper chest that has nothing to do with posture. The subsonic pressure is more pronounced here at the open chassis. The vibration is no longer mediated by the Mylar damping layer, and his sternum registers it now as well as his forearms. Not painful, not dangerous by any metric he can measure, just present, the way a strong current of water is present against your leg when you are standing in a river, a physical fact that the body acknowledges before the brain does. He breathes. He goes back to the wires. The entire primary bus of the LRV-002 has been rewired from the inside out. Thorne straightens and looks at the open chassis. He looks at the UV pulsing coating on the terminals. He looks at the Mylar panels in the specimen tray, pristine, preserved, as if they had been protecting something that needed to remain sealed for exactly as long as it took for the work inside to complete. He looks at the crystalline conductors glowing with their faint interior light, carrying zero current, transmitting something that doesn't have a name in the facility's instrument suite. He picks up the marker and writes on the whiteboard beneath last night's entry, "Primary bus, copper replaced, crystalline material, intact PVC jackets, zero thermal signature." He draws a line under it, then he says it out loud, the way he says things when they need to be in the audio log. NASA didn't build this. They built the shell, something else moved in and rewired the house. Sully has stopped filming. She is standing at the rear of the chassis with the UV wand still in her hand, looking at the coating on the battery terminals, and she has the expression of someone running a calculation that keeps returning an answer she doesn't want. Elias. Her voice has gone to the careful, flat register. How long does it take to replace copper with crystal at a molecular level? If you're doing it wire by wire, inside an intact PVC jacket, without breaching the jacket surface? I don't know. It's not a process that exists. Right. So however long it took. She pauses. It wasn't engineering. It wasn't manufacturing. It was something that doesn't have a process time, because it's not a process we have a name for. She looks at the rover. Whatever did this didn't need a lab. It just needed time. 55 years in a sealed storage case. She finally puts down the UV wand. While everyone thought this thing was a dead museum piece, Thorne thinks about the chain of custody. The rover was logged out of NASA Johnson long-term storage 31 days ago. Before that, it had not been touched in 11 years. The last pre-loan inspection was a visual and photographic survey, no disassembly, no probe contact. Before that inspection, the record gaps are significant. Transfers between facilities. Storage in 3 different warehouses over 5 decades. He pulled the full custody history when the project was authorized, and it had the usual look of NASA archiving from the 1970s onward. Meticulous until the budget cuts, sporadic after, adequate by bureaucratic standard and meaningless by forensic standard. There are 18-month windows in that record where the rover's precise storage location is a building name and nothing else. 18 months. More than enough time. But that framing still assumes a starting point. A 0 hour. The spectrum analyzer marks another 1.2 Hz cycle. The crystalline conductors glow their steady faint glow. The UV coating pulses with it, the whole system synchronized, the whole rover operating as a single coherent unit, under physics that none of their instruments can fully characterize. Thorne goes back to the whiteboard. He writes one more line under the last entry. Duration of modification, 55 years. Location, sealed NASA storage. He stares at it. He has been thinking about this as a contamination event, something that got into the rover at some point and did something to the hardware. That framing has a timeline that starts somewhere after the Apollo program ended, somewhere in the chain of custody between the lunar surface and this clean room, some point of compromise where an unknown material entered the sealed storage case. But that framing requires a starting point. A 0 hour when the rover was clean, when the copper was still copper, and the Mylar was still new because it had just been installed. The Mylar was new because it had just been installed. The Mylar was installed before the rover shipped to the moon. He writes one more line. Modification may predate storage. Assess. Was this done before launch? The air filtration cycle resets. The room breathes. If this was done before launch, it was done in this building, or one very much like it, in a NASA clean room, by hands in cotton gloves who thought they were doing final QA on a lunar rover, checking boxes on a manifest, signing off on a dead machine that was going to drive across the moon and never come back, or by something that was already in the building and knew what the rover was going to touch when it got to where it was going and made sure the rover was ready to receive it. Thorne looks at the chassis, the dead man's handlebars, the empty seats, the communications dish angled at the ceiling. He is no longer certain this machine was ever dead. And the insulation in the specimen tray, supple, undegraded, adhesive, still tacky after 55 years, has one more thing to tell him. He picks up the nearest panel, runs his thumb across the adhesive face, still tacky. But when he checked the panel before he removed it, the Mylar was sealed tight to the chassis. No gaps, no separation at any edge. He ran the UV wand over the exterior during yesterday's initial inspection and found nothing. No outgassing, no off-gassing from degraded polymer, no chemical signature at the seam lines. The adhesive was active, the seal was perfect, and the signal was inside. The Mylar wasn't aging because it had a job to do, and the job isn't finished yet. He adds a final line to the whiteboard. Insulation function. Containment, not protection. Signal, previously suppressed. Sully reads it. She is quiet for a moment. Then, if the Mylar was suppressing the signal, then whatever is receiving this signal got a stronger feed the moment we started pulling panels. She sets down her stimulant can very carefully. We've been amplifying it. Every panel we removed, we opened the aperture. Yes. So what we're seeing on the analyzer right now is a louder signal than whatever was transmitting before we arrived. Louder and cleaner. He looks at the open chassis, the full power version. She looks at the spectrum display. The 1.2 Hz fundamental is unchanged. Same frequency, same harmonic series, the same metronomic precision it has held since the moment the LiDAR scan first caught the chassis tremor. But the signal amplitude is 4 decibels higher than it was at the start of the shift, before the first Mylar panel came off. 4 decibels. Not a significant number in isolation. Significant as a rate. 12 panels removed over one shift. 4 decibels of gain. If tomorrow's probe work opens the chassis further, if the telemetry relay housing comes off, if the bus bar connections are exposed, the trajectory of that number becomes a different kind of problem. Tomorrow we probe the bus, Thorne says. It is not a question. The schedule requires it, the data requires it, and the protocol requires that they follow the data wherever it goes. That is the job. That has always been the job. Sully is looking at the crystalline strand he left exposed on the bench, the section he scored free of the primary bus, now sitting under the magnification lamp still glowing faintly with its interior light, conducting something nameless through its translucent body at ambient temperature. When we probe the bus, she says slowly, and the probe makes contact with one of these. She gestures at the strand. We're not probing a wire. We're not introducing a measurement instrument into a passive circuit. She looks at him. We're plugging something in. He knows. He has known it since he answered the phone in the log at 0217 yesterday morning. He knows what the contact will mean and what it will register on the other end and what the signal will do in response. He knows they have to do it anyway, because that is what the data requires, and that is the job. And whatever is at the other end of this signal has had 55 years to prepare for exactly this moment. Thorne caps the marker and sets it on the whiteboard tray. Tomorrow they probe the bus, and when the probe makes contact, the conversation starts. Chapter 3. The Probe Breach. The probe touches the crystalline bus at 0914, and the facility's digital clocks jump forward by 3 seconds simultaneously. Thorne does not notice. He will not notice for another 40 minutes when the discrepancy surfaces in the facility log during a routine timestamp audit, and he spends 10 minutes verifying it against 3 independent sources before he accepts it as real. 3 seconds. Every clock. Simultaneous. No external correction event, no NTP synchronization pulse, no instruction from any network system. Because the air gap protocol closed every network connection in this room before the probe made contact. The clocks moved on their own at the moment of probe contact, each by a slightly different margin, and then resumed normal operation as if nothing had happened. He will file that in the log, and he will not mention it to Sully yet because he does not have an explanation, and he does not offer data he cannot explain. Right now, he is watching the spectrum analyzer. The 1.2 Hz fundamental is gone. In its place, a wall. Full band spectral saturation from 2 Hz to 40 GHz, every channel pegged to maximum. The display rendering as a solid white block because the analyzer does not have a color for a signal this dense. Not broadband noise. Noise is structureless, an undifferentiated smear of energy across the spectrum. What the display is showing has geometry. A regularity in the energy distribution that Thorne can see even through the saturation. The same organized architecture that characterized the baseline 1.2 Hz pulse but expanded, replicated simultaneously across every frequency band, as if the signal has been running in low-power standby for 55 years, and this probe contact is the first thing worth waking up for. The chassis is transmitting at full power. Contact mic. Audio out. Sully hits the attenuator. The output comes through the ceiling monitors. Structured, high frequency, a rapid sequence of tonal pulses cycling through a fixed vocabulary of discrete pitches. Not noise, not distortion. A transmission, dense, layered, organized, each cluster of tones differentiated from the last, the pattern repeating and varying with the regularity of something that is encoding information rather than venting charge. Thorne counts clusters. The pattern does not loop. Every cluster is distinct. Whatever the signal is carrying, it has more to say than it has said so far. It runs for 11 seconds. Then it stops. The spectrum display clears. The 1.2 Hz fundamental returns, metronomic and precise, as if the last 11 seconds did not happen. The chassis settles into its baseline throb. The ceiling monitors go quiet. Thorne's sternum is ringing, a residual vibration from the burst, higher frequency than the baseline, the physical echo of 11 seconds of full-band transmission passing through the copper mesh of the walls. He notes the duration, the frequency character, the clean return to baseline. Then he looks at Sully. Her hands are still on the keyboard. She has not moved them since the moment of probe contact. She is staring at the capture display with the expression she gets when the data has said something she needs a moment to accept before she responds to it. Tell me the recorder held. Full fidelity. 11.3 seconds of capture. She exhales. Her fingers start moving, fast, uneven, the rhythm she uses when the data is running faster than the plan. Okay, pulling the packet structure on the burst. It's layered. I can see the encode passes. There are discrete data units in here. It's not continuous. Wait. She stops. Starts again. Wait. Elias, the burst has a header. Same architecture as the baseline signal. No, it's different. The baseline has the 2026 AES variant, and this burst, she pulls up a comparison window. Her voice drops a register. This burst has a 2026 header that is structured as a response to a specific initiating packet. She turns her chair to face him. Our probe has a standard factory handshake. Every high-sensitivity probe on the market outputs the same 3-byte identifier on first contact with an unknown terminal. Manufacturer ID, device class, contact timestamp. She looks at the spectrum display. This chassis just answered that handshake. It returned an acknowledgement packet containing our probe's identifier, reflected back at us inside a 2026 encrypted wrapper. A pause. From a 1971 hardware system that was drawing zero current 30 seconds ago. Thorne looks at the probe. Tip still in contact with the crystalline strand on the bench, the section he separated from the primary bus yesterday, sitting under the magnification lamp, glowing its faint interior glow. The analyzer shows the 1.2 Hz baseline. Steady. Pull the probe. She pulls it. The signal holds. No change. The crystal strand continues its luminescence. Same intensity as before contact, and the spectrum shows only the familiar fundamental and its harmonic series. Unchanged. The system registered the probe, generated a response, and resumed baseline operation. The behavior of a functioning terminal when a recognized device disconnects. It didn't loop, Sully says. Her voice has the careful flatness of someone reconstructing what they witnessed into language precise enough to stand up to later scrutiny. A looped signal returns an identical packet regardless of input. What we got back was specific to our identifier, manufacturer, device class, timestamp, all reflected back. The signal parsed our probe's output and generated a response keyed to that specific input. She looks at the strand. That's not a recorder. A recorder doesn't read its audience. No, so it's a live system, running a real-time response protocol. It received our handshake. It decoded it. It generated a return packet. It encrypted the return in a format our analyzer can receive. She stops herself. She is going fast, and she knows it, and she slows it down deliberately, like someone gripping a railing. It's not broadcasting a loop. It just recognized our probe's handshake protocol. It's aware. The air filtration cycle completes. The room exhales. Thorne looks at the whiteboard. He writes, burst on contact, handshake response, identifier specific, not a recording. He stares at it. 20 years of this work. Every impossible reading has been a hardware artifact. Inductance, coupling, bad grounds, degraded insulation producing phantom signals in adjacent conductors. He has a methodology, and the methodology has never failed him. Observe, isolate, eliminate, confirm. The reading is always explicable when you go far enough down the chain. The chain ends here. The chassis received a 3-byte identifier from an instrument that touched it for 11 seconds. It decoded that identifier. It generated a cryptographically structured response. It transmitted that response in a standard that does not yet exist as a published specification. It did all of this before Thorne had time to form a conscious intention to pull the probe. There is no artifact on the list that reads, comprehends, and responds. That is not what artifacts do. Run the outbound trace, he says. The response packet went somewhere. Find the destination. Already running. Stream of consciousness register now. Half narrating for him, half for the record. Outbound trace on the burst. Destination address in the packet header. It's inside the encryption, but the routing field should be visible. I've got the field boundary. It's long, way longer than a standard IP header. She highlights the field on screen. This isn't a network address. Not a server, not a relay, not a satellite uplink. A pause. The analyzer hums. It's a coordinate set. 3-axis, long precision. The kind JPL uses for interplanetary ranging, meter-accurate localization at lunar distance. She does not turn around. The response packet is addressed to a fixed point 238,000 miles from this room. The pulse ticks, 1.2 hertz, 67 times per minute. Cross-reference the coordinates, Thorne says. Keyboard. A pause. Then, Hadley-Apennine, Mare Imbrium, eastern edge. A longer pause. That's the Apollo 15 landing site. That's where this rover drove. The clean room hums and breathes and does its job. The crystalline strand glows on the bench. The baseline signal marks its steady intervals, and the contact mic carries its subsonic throb through the floor and the walls and up through Thorne's skeleton to the place in his sternum where it has been sitting for 3 days now. He picks up the marker. He adds one line under everything else on the whiteboard. Outbound destination, Hadley-Apennine. Live address. Response sent. He looks at the rover, at the communications dish angled toward the ceiling, toward the sky, toward a fixed point, 238,000 miles north-northwest. At the terminal housing, open, the crystalline conductors exposed and glowing. The rover has not been broadcasting into a void. It has been in correspondence. Every probe contact triggers a new response. Not the same response, a new one, keyed to the specific instrument, the specific identifier, the specific timestamp. It knows what is touching it. It reports that information to a receiving station at the Apollo 15 landing site. It has been doing this since before anyone in this building was born, running on zero measurable current, maintaining an encrypted correspondence with a location on the lunar surface that no human being has visited in 54 years. Sully is running the payload decode on the transmitted packet. Not the header, the contents. What the rover actually sent to the moon in response to their probe contact. She has been quiet for 90 seconds, which is long for her, and Thorne crosses the room to look at her display. The payload is not an acknowledgement token, not a handshake completion flag. It is a structured data block organized into discrete fields, integer sequences, floating point arrays, a binary string she is running against the decode library. She finds the match quickly. The match is not obscure. What is it sending? Thorne asks. She pulls up the floating point arrays, checks the value ranges against the reference tables, looks at the field labels. Biometric data. Her voice is very level. Heart rate, core temperature, respiratory rate, blood oxygen saturation. She looks at the field structure, then at him. When our probe touched this chassis, the rover took our biometric readings and transmitted them to the moon. The air filtration exhales. Thorne does not move. He looks at the rover, at the exposed bus housing, at the crystalline conductors running from the telemetry relay to the communications dish, the full transmission chain of a machine built to carry 2 men across the lunar surface and relay their physiological data back to mission control in Houston. It took their biometrics, without announcement, without request. At the moment of probe contact, while the burst was firing and the spectrum display was saturated and both of them were watching instruments, the rover sampled them, logged their biology, packaged it into a structured telemetry block, transmitted it to a receiving station on the moon that is still apparently receiving, the same way it sampled the 2 men who sat in its seats in July of 1971. The same station that received Dave Scott's heart rate on the lunar surface is now receiving Thorne's. He stands with that for a moment. Not panic. He does not have the luxury of panic, and it would not be useful if he did. He has the data, and he has the methodology, and the methodology says you go down the chain until you find the physical mechanism that explains the reading. The chain here is, probe contact triggers full band transmission burst. Burst contains outbound data packet. Packet destination is lunar coordinates. Packet payload is biometric telemetry logged at moment of contact. Each link in that chain is verifiable. Each link has been verified. The chain is real. What the chain means is a separate question, and it is not one he can answer tonight. He files it in the same column he filed the zero current readings and the pristine Mylar and the crystalline conductors and the 2026 encryption header, the column headed by impossible, which he has been working through 1 entry at a time for 3 days. The column is not getting shorter. Every answer opens 2 more questions, and the questions are getting larger. and the methodology that has served him for 20 years is beginning to feel like a flashlight in a space with no walls. Sully has gone quiet at her station. She is looking at the biometric payload on her screen, at Thorne's heart rate and core temperature and blood oxygen saturation, logged without his consent by a 55-year-old rover and transmitted to the moon in a packet that arrived at its destination before he had finished processing the fact that it was sent. She has the expression she gets when she is deciding whether a thing she is about to say sounds credible enough to say out loud. "It sampled us," she says, "the same way it sampled the crew." She looks at the rover. "We're in the data set now." Thorne does not answer. There is no answer that makes the data smaller. "Close the air gap," he says. "Every instrument that has touched this chassis. Physical disconnect. No software toggle." She is already pulling cables. He looks at the whiteboard, at the column of entries that started with 0 current. Active signal. Source. Unknown 3 days ago, and has grown one line at a time into something he does not have a framework for yet. Tomorrow they put the rover in the Faraday cage. Not to stop the signal. The signal does not need the cage's permission to propagate. He established that on day 1 when the baseline pulse persisted through a full facility power down. He is putting the rover in the cage to find out what the signal does when the cage's copper mesh gives it something to work with instead of something to push against. He has a theory. The theory is that the cage will not contain it. The theory is that the cage will feed it. He does not want to be right, but the data has not given him the option of being wrong yet, and he does not expect that to change tomorrow. What he knows: the Faraday enclosure blocks electromagnetic propagation. It does not block whatever this signal uses as a carrier. The baseline pulse propagated through the cage mesh on day 1 without attenuation. If the mesh does not stop the signal, the mesh may interact with it. And a copper mesh in contact with a signal that treats conductors as transmission media is not a cage. It is a resonator. It is an antenna. He is about to put a 55-year-old lunar rover, currently in active two-way communication with the moon's surface, inside a copper antenna, and close the door. He adds a final line to the whiteboard. Faraday test. Attenuation or amplification. Verify before entry. He draws a box around it, not a line. A box. The kind he uses for action items he does not want to miss. He is going to miss sleep instead. Chapter 4. The neutral zone. The cage goes sealed at 0800 and the signal gets louder. Not subtly louder. The spectrum analyzer registers a 42% amplitude increase the moment the last copper mesh panel locks into its grounding rail. 42% in under a second, a jump so clean and immediate that Thorne checks the instrument calibration twice before he accepts it. The Faraday enclosure is doing exactly what a Faraday enclosure does. It is providing a low-resistance path to ground for every conductor in the room, and the signal is using that path. The cage that was supposed to contain it is feeding it instead. He writes on the whiteboard, Faraday, plus 42% on seal. Resonator confirmed. He draws the box around it that he drew last night, and it already has a box, so he draws a second one. Ghost is riding the mesh, Sully says from the monitor bank. She is 3 coffees in, and her voice has the bright-edged quality it gets when she has been awake too long and the data has been too strange for too many consecutive hours. It's not fighting the cage, it's drafting off it. The enclosure grounding rail just became a relay station. Her fingers are moving. Bit depth on the signal is, Elias, the bit depth is climbing. It was holding steady at something like a 24-bit equivalent for 3 days, and right now it's past 32. It's still moving. Rate? Fast. 1 bit equivalent per 6 seconds approximately, still climbing. It's like something just got a better connection and it's pushing more data through because it can. She pauses. We gave it a better antenna. We literally just handed it a better antenna and closed ourselves inside it with the rover. Thorne looks at the chassis. On its platform at the center of the enclosure, the crystalline bus conductors visible in the open terminal housing. The UV reactive coating on the bus bars pulsing its 1.2 Hz rhythm. The communications dish aimed at the mesh ceiling. Close now. 2 meters of air between the dish and the copper grid. 2 meters between the rover's transmitter and the antenna they have just given it. He should have modeled this. He ran the theory last night, and the theory said amplification, and he ran the theory again before he opened the door this morning, and it still said amplification, and he put the rover in the cage anyway, because the protocol requires empirical verification, and empirical verification requires doing the thing that might be wrong and finding out. The thing was wrong. The data is clear. He logs it and moves forward. High-speed cameras live. Both units. Frame rate at 10,000 per second. Wide field on Unit 1, tight field on Unit 2. Tight is centered on the telemetry relay housing. That's where the original circuit gap is. She pulls up the live feed from Unit 2 on her secondary display. Nothing visible yet, just the relay housing and the connector block. The relay housing. Thorne crosses to the chassis and crouches at the front left quadrant where the telemetry relay block sits on its mount. A component roughly the size of a hardback book, original Boeing fabrication, aluminum housing with a phenolic connector block on the face, and a wiring harness running back to the communications stack. The wiring harness is the crystalline replacement wiring, of course. Every conductor in this chassis is. And under the cage lighting, the harness glows its faint interior glow as it curves from the relay block back along the spar toward the CLU. In the original design, the relay is a passive switching element. It takes the signal from the Fairchild Semiconductor 709 operational amplifiers in the CLU, routes it to the correct antenna element, and does nothing else. A gate, a path. Between the relay output terminal and the antenna feed connector, there is a gap. He has seen it in the inspection photographs. A small discontinuity in the circuit, approximately 3 millimeters, where the relay output lead does not quite reach the antenna connector pin. In a functioning circuit, that gap would be bridged by a solder joint. In the LRV-02, the solder joint is absent. It was absent in the original build photographs from 1971. It has always been absent. The circuit has always had a 3 millimeter break in it, and the circuit has transmitted anyway, for 55 years, through lunar surface operations and storage and transport, and 3 days in this clean room. And nobody in any of those 55 years logged it as an anomaly, because the rover transmitted perfectly, and a working circuit is a working circuit, regardless of what the schematics say. He had assumed it was a photographic artifact, a shadow in the build documentation, a connector that was harder to see than it looked. He did not go looking for the gap because the gap had an obvious explanation. Standing inside the Faraday cage at 42% signal amplification, he looks at the gap now under the magnification loop and accepts that he was wrong. The gap is not empty. There is something in the 3 millimeter space between the relay terminal and the antenna connector. Something he could not see in photographs. Something that did not show up in the initial LiDAR geometry because it is smaller than the scan resolution. Something he is only seeing now because he is close and the magnification is high and the signal amplitude is 42% stronger than it was 40 minutes ago, and whatever is in the gap is active. It looks like interference, like the visual artifact you get when you look at a heat shimmer above asphalt in summer. A refractive distortion, a bending of the light passing through that space, as if the air in the 3 millimeter gap has a different optical density than the air around it. But the room temperature has not changed. There is no heat source at the relay housing. The thermal probe reads ambient throughout. It is not heat shimmer. It is something else bending the light. Sully. Tight camera on the relay gap. What do I have? He hears her pull up the high-speed feed, and then he hears her stop talking, which is more informative than anything she might have said. The gap is... She stops. Starts. There's a visual distortion in the gap. Not in the connectors, not in the housing, specifically in the space between the relay terminal and the antenna pin. It's refractive. It's bending the background image. A pause. At 10,000 frames per second, it looks like the distortion is pulsing. 1.2 hertz. The optical distortion in a 3 millimeter air gap is pulsing in sync with the signal. What else? What else? The distortion boundaries are not stable. At 10,000 frames, the edges of the distortion region are moving. Not smoothly, discretely. Frame to frame, the boundary jumps position. It's quantized. The distortion occupies a specific region and then it occupies a slightly different specific region, and there's no continuous movement between them. It relocates. Her voice has gone up a quarter register. Elias, the material in that gap is not behaving like any state of matter I have reference data for. Solids, liquids, gases, plasma, all of them move continuously. This is moving discontinuously. It's jumping. Frame rate. Push to maximum. The high-speed cameras go to 50,000 frames per second. The processing lag on the live feed goes up. The display is now running on a delay as the buffer fills. Thorn holds his position, crouched at the relay housing, looking at the shimmer in the gap without the magnification loop now, looking with his eyes, and what he sees is nothing. With the naked eye, the 3mm gap looks empty. The distortion is below the threshold of unassisted human vision. Whatever is in there is smaller than his ability to perceive it directly. That does not make it smaller. It makes the gap more frightening. Feed is processing. Sully's keyboard. Buffering. Okay, I've got the 50,000 frame capture pulling the first pass. Elias. A very short pause, the kind she uses when she needs a half second to decide to say a thing out loud. The material in the gap is phasing. At 50,000 frames per second, the distortion region is present in some frames and absent in others. Not just relocated. Absent. The optical distortion disappears from several consecutive frames and then reappears. The material in the gap is periodically not in this room. She says the last sentence with the flatness of someone reading a measurement off an instrument that cannot be wrong. I don't mean it's moving too fast to image. I mean it is not physically present in this space during those frames, and then it is again. The air filtration cycle turns over. The sound of it is prosaic and small and belongs to a different kind of room than this one. Thorn straightens. He looks at the relay housing, at the 3mm gap between the terminal post and the antenna connector pin. A gap that has been in this circuit since before the rover went to the moon. A gap that should have prevented the circuit from functioning. A gap through which the signal has been propagating for 55 years without a conductor. The signal does not need a conductor, it needs a gap. The Faraday cage, he says. Why did it amplify the signal? Because the cage is grounded copper mesh and the signal. She stops. He can hear her arriving at the same place he arrived 30 seconds ago. The signal isn't electromagnetic. We've known that since it didn't attenuate behind the shielding. It propagates through the gap without a conductor because it isn't using the conductor. It's using the gap, the space between the conductors. A pause. A Faraday cage is not a sealed room. It's a series of very small gaps, the mesh apertures. We put the rover inside several thousand small gaps and told the signal here are more paths. More gaps, more propagation paths. It's using the mesh the same way it uses the relay gap, as a medium. Her voice has gone very quiet and very fast simultaneously, the combination she hits when she is scared and keeping the fear subordinate to the analysis. Elias, a Faraday cage has a specific mesh aperture size. Ours is rated to block signals above a specific wavelength. The signal gets through because it's not propagating as a wave. It's propagating as a series of quantum jumps through discrete spatial gaps. It is literally tunneling through the mesh aperture by aperture. She looks at the rover from across the enclosure. It's using the rover as a bridge, not between locations, between states of matter. Thorn writes it on the whiteboard. Then he writes the implication under it, because the implication follows directly, and he needs it in the log. Propagation. Medium, spatial gaps, not conductors. Faraday apertures. Relay nodes. Signal is tunneling. The bit depth counter on Sully's monitor has been climbing the entire time they have been talking. It is past 40 now, still moving. The phase-out frames, Thorn says. When the material in the gap disappears, where does it go? She is already running the cross-reference, the high-speed footage with the signal data with the timestamp log. She runs it for 90 seconds and Thorn watches the bit depth counter and does not rush her. During phase-out frames, the outbound signal amplitude spikes, she says. Every time the material drops out of our physical space, the transmission power goes up. It's not disappearing. It's going somewhere with lower resistance than this room. It's taking the path of least impedance, and the path of least impedance is not in this room. She pulls up the spike correlation on screen. The alignment is exact, frame by frame. Every absence corresponds to a transmission spike. Every return corresponds to a signal dip. When the material phases out of our space, it is propagating through whatever space offers less resistance to its signal, and when that propagation is complete, it phases back. She stares at the correlation graph. It's using our physical reality as a waypoint. It's stopping here because the rover's chassis is here, not because here is the destination. The 1.2 Hz pulse ticks in the copper mesh of the cage walls, in the floor, in the bench surface under Thorn's hands. The entire enclosure is vibrating with it now, every conductor in the cage carrying the signal, the cage doing exactly what it is designed to do, and the signal using that against them. Thorn looks at the relay gap, at the 3 millimeters of space between two connectors that should be joined and have never been joined, and through which something is periodically leaving this room. He straightens and becomes aware of two things simultaneously. First, the subsonic pressure that lives in his sternum has changed character inside the cage. It was omnidirectional before, a field effect emanating from the chassis in every direction equally. Now it has a directionality. It is coming from the relay housing specifically, from the gap, a focused pressure that tracks when he moves, staying oriented toward that 3 millimeter interval, regardless of where he stands. Something in that gap knows where he is in the room. Second, his breath is not fogging. It should be fogging. The thermal probe in his hand reads 65 degrees, 3 degrees below the room's baseline, a small drop but a measurable one, and at 65 degrees in still air, a person's exhaled breath should produce a faint visible condensation. He exhales deliberately. Nothing. The exhaled air vanishes without condensing. The moisture going somewhere, the thermal energy going somewhere, and the somewhere is not the air in this enclosure, because the air in this enclosure is getting colder. He writes the final line on the whiteboard. Rover, anchor, relay, gap, transit point, thermal draw active inside cage. Then underneath it, destination unknown. He looks at Sully. She is looking at the bit depth counter. It has passed 48 and the rate of climb has not slowed, and she has been watching it the same way you watch a pressure gauge on a system you are not certain is rated for the current load. How long until we have to open the cage door, she says. Not a question about timing, a question about whether they should. Thorn looks at the counter, looks at his own breath, absent in the cold air. Looks at the relay housing with its 3 millimeters of space where a solder joint should be, and something else is instead. Something that phases out of this room and back again, using the chassis as an anchor, using the cage as a resonator, using the gap as a door that has been built into this machine since before it ever left the ground. Now, he says. She is already moving. He follows her, and the directional pressure from the relay gap tracks him the entire length of the enclosure. And when the cage door swings open and they step through and the signal amplitude drops back to its pre-cage baseline, the first thing Thorn does is check his own breath. It fogs. He stands in the doorway and watches his own breath fog and does not say anything about it. And the rover sits on its platform 6 meters away in the copper enclosure that is still resonating with its signal, and the relay gap is still doing whatever it is doing, and the bit depth counter on Sully's display has stopped climbing. It has not dropped. Whatever headroom the cage gave the signal is keeping. Chapter 5. The Spectrum Ghost. The signal isn't a wave, and Sully has been staring at the proof for 3 hours before she can articulate why that matters. She pulled the visualization suite online at 0640 before Thorn arrived, because she could not sleep, and the data on her laptop was doing something she had never seen a signal do, and she needed the full display array to look at it properly. The suite runs the signal through a 3-dimensional rendering engine, a tool she uses to find structure in complex waveforms, to visualize topology that reads as noise in 2 dimensions. She has used it for 6 years, She knows what signals look like when you rotate them in space and let the engine find the geometry. Waveforms extend along axes. A periodic signal becomes a helix. An amplitude-modulated signal becomes an envelope. A frequency-modulated signal becomes a stretched spring. The physics of the transmission is always recoverable from the shape. You look at the render and you understand how the signal was made. The 1.2 Hz signal does not extend along any axis she assigned. It renders as a closed solid, a three-dimensional geometric form fully enclosed, its surfaces defined by the signal's own internal structure rather than by frequency or amplitude or time. It is not using her axes, it has its own. And the form it produces is not a shape from any signal class in her reference library, not a natural geometry, not a crystallographic form, not a mathematical primitive she recognizes. It is specific. It is detailed. It is, and she has been resisting this word for 3 hours, architectural. A complex of nested and connected forms with a spatial logic that her pattern recognition keeps wanting to call intentional. And she keeps telling her pattern recognition to be precise. And her pattern recognition keeps coming back with the same word. She has printed a still frame and taped it to the wall. Next to it, she taped the NASA topographic chart of the Hadley-Apennine sector she pulled from the Planetary Science Repository. The Apennine mountain range curving along the eastern margin in a long arc, Hadley Rill cutting its sinuous channel north to south across the Mare surface, the flat basaltic plain where Apollo 15 set down in the lower left quadrant. She drew alignment lines between the render and the chart in red marker, matching the geometric features of the signal to the topographic features of the surface. She drew 14 lines. All 14 are exact, not approximate. Exact within the resolution of both images, the signal geometry corresponding to the lunar surface topology at a precision that is not a coincidence and is not a projection artifact and is not something she can explain by any signal processing error she has ever encountered in 6 years of this work. The render is not a representation of the Hadley-Apennine site. The render is the Hadley-Apennine site. Real-time, current, updating 67 times per minute with data that is 67 times per minute accurate. She is still looking at the alignment lines when Thorne comes through the door. "The signal is a map," she says, before he has his coat off. "Not metaphorically. The geometric structure of the signal encodes a three-dimensional spatial representation of the Hadley-Apennine landing site. I've been running overlays for 2 hours against NASA surface topology data, and it fits. The rover is transmitting a three-dimensional map of its own parking spot." He looks at the display, at the slowly rotating solid, at the red alignment lines on the wall. He does not say anything for a moment. "Continuously?" "Continuously. It's not playback. The geometry updates. I've been watching it for 3 hours, and it has changed 4 times in ways that correspond to real surface conditions. Thermal gradients, albedo shifts. It's pulling current data from the Hadley-Apennine site and encoding it into the carrier signal in real time." She gestures at the render. "The 1.2 Hz isn't a heartbeat. It's a frame rate. The signal is updating this map 67 times per minute." Thorne looks at the rover, visible through the visualization suite's observation window, still on its platform in the Faraday cage, the cage door closed after yesterday. The communications dish angled toward the ceiling. 67 updates per minute for however long this has been active. 55 years of continuous real-time lunar cartography running through crystalline conductors on zero measurable current. "What's it mapping toward?" he says. "The cage is blocking outbound transmission." "No." She pulls up the signal strength log from yesterday. "The cage amplified the signal. It didn't block outbound. We verified that. The cage gave the signal a better antenna. Whatever it's been transmitting to Hadley-Apennine, it was transmitting through the cage walls. We just made it louder." She looks at the alignment chart. The map is live, the destination is live, and nothing we've deployed has interrupted it. The air filtration cycle turns over. The room breathes. Thorne crosses to the monitor bank and pulls up the audio analyzer. The contact mic feed, running continuously from the chassis spar. The 1.2 Hz baseline. the subsonic throb he has catalogued for 4 days. He runs the frequency analysis out to the upper range and finds it immediately. A high-frequency component, almost inaudible, a rhythmic chittering near the ceiling of human hearing, timed precisely to the frame rate of the render, present between each pulse like a mechanical shutter firing between exposures. You've been hearing that? Since 0640. Sully's voice is careful. I didn't turn up the gain because of what happened yesterday in the cage. The directional pressure from the relay gap. I wanted to be conservative. Turn it up. 3 decibels. She turns it up. The frequency hits the back of Thorne's sinuses before it registers in his ears. A resonant coupling, the specific unpleasant sensation of a frequency that some structure in the human skull has a natural response to, something between a developing headache and a sudden pressure change in a descending aircraft. His stomach turns over once, a brief rolling nausea that is gone before he can fully register it. The molars on his left side ache faintly. At the edge of his vision, in the peripheral field only, he catches a texture. Not darkness, not light. A fine-grained visual static, present for less than a second, fading the moment he shifts his gaze toward it. He does not look away from the monitor. He keeps his eyes forward and tracks it in his periphery, and in the half-second before it fades, he has the impression that the static is not random, that it has a geometric structure, that it is not noise, that it looks like the render. Down, he says. She brings it back to baseline. The nausea clears. The toothache fades over 5 seconds. He notes both in the shift log without comment. The static, she says. Both times I've pushed the gain, the same peripheral visual artifact. I've been trying to characterize it, but it resolves too fast. She pulls up the acoustic spectrogram. The audio is the map in sound. The chirp pattern is topographic data translated into frequency. The signal is producing an acoustic version of the 3-dimensional render simultaneously with the geometric version. That's why the nausea. It's not an audio signal below distress threshold. It's a gravitational carrier with an acoustic component, and the acoustic component is encoding spatial information that the human auditory system is not equipped to process. We hear it as nausea because the data doesn't have a perceptual format in our neurology. She looks at the display. We're hearing the surface of the moon. Our bodies treat it as an error. The gravity sensor, Thorne says. He is looking at the secondary display where she set up the interferometric sensor before his arrival. Yes, look at the trace. He looks. The sensor is reading a structured oscillation in the local gravitational field. Not the noise floor, not seismic artifact, not building vibration. A clean periodic signal in the microgravitational range, organized and deliberate, each cycle corresponding to a frame update in the render. He checks the timestamp alignment. It is exact. The gravitational fluctuation and the render update are the same event, expressed simultaneously in 2 different physical domains. The signal modulates local gravity, he says. At microscale. Nanogal amplitude. Not enough to feel, not enough to affect anything in the room, but measurable, structured. The geometry we're seeing on the render is not a representation of a gravitational phenomenon. It is the gravitational phenomenon. She turns her chair to face him. The signal is not using electromagnetic propagation. There's no EM carrier. The encoding medium is a modulated perturbation in the local gravitational field, the 1.2 Hz pulse, the 3-dimensional geometric structure, the acoustic chirp, the map of Hadley-Apennine. All of it is gravity. We've been running spectrum analyzers on a signal that doesn't use the electromagnetic spectrum. She holds his gaze. That's why the Faraday cage can't stop it. That's why the shielding can't stop it. That's why our probes read zero current in conductors that are clearly active. Every instrument we've been using measures the wrong physical quantity. She gestures at the render. This isn't an EM broadcast. It's vibrating the fabric of the room. We aren't listening to a radio. We're listening to a pulse in space-time. Thorne looks at the render, at the architectural form rotating on the display, at the 14 red alignment lines on the wall. He thinks about the relay gap, The 3 mm interval in the telemetry circuit where a solder joint should be and isn't. Where something phases in and out of this room at 50,000 frames per second, present in some frames and absent in others, briefly occupying a space with lower physical resistance than this one before returning. A gap in the physical medium. A discontinuity in the conductor. He has been thinking about it as a flaw in the circuit, a place where the signal jumps without a wire. Gravity does not need a wire. Gravity propagates through the gap between things, through the space that conductors do not occupy, through the vacuum between atoms, through the interval between the relay terminal and the antenna pin, through the mesh apertures in a Faraday cage, through the walls of a building, through the ground. The relay gap is not a missing solder joint. It is a tuned cavity, a physical aperture calibrated to a specific gravitational wavelength, built into this machine before it shipped to the moon, designed from the beginning to emit a signal that would pass through every electromagnetic instrument ever pointed at it without leaving a trace. 55 years of periodic NASA inspection. 20 different engineers. Not one anomaly logged at the relay gap. Because they were looking at the wrong physical quantity. How long has this propagation been active? He says. Specifically, prior to our probe contact 2 days ago, was the gravitational signal present before we touched the chassis? She pulls up the gravity sensor retrospective. She has been running the sensor for 10 hours, but the facility's seismic monitoring infrastructure has been logging microgravitational data as a baseline function for 11 years. It logs passively, automated, stored in the facility's archival system. She ran the retrospective analysis against the archival logs before he arrived. She puts it on screen. The 1.2 Hz gravitational oscillation appears in the archival data at the date of the rover's delivery to this facility, 31 days ago. Clean, structured, present from arrival. She scrolls back further, to the year before delivery. Noise floor, no signal. Delivery date, signal present, immediate, as if it was already running when the rover came through the door. It was active on arrival, Thorne says. Active on arrival. And if it was active in storage, if it was active anywhere the rover has been for 55 years, then the gravitational record of every facility that housed this machine would show the same oscillation, if anyone had been running sensitive enough instrumentation. Nobody runs interferometric gravity sensors in a storage warehouse. She looks at the archival log. Nobody was looking for this because nobody knew what to look for. The signal has been here the entire time. We just built the instrument that could see it. The render updates. 67 times per minute. The acoustic chirp fires between frames. Subsonic in the room now. The gain back at baseline. The nausea absent. The gravity sensor marks its micro-fluctuation. The rover sits on its platform in the copper cage that made it stronger. We need the CLU, Thorne says. The shadow logic architecture. Whatever is running the map rendering and the gravitational encoding. We've been working inward from the chassis surface. We need to go deeper. The endoscope. The endoscope. The CLU core. He looks at the rover through the observation window. Whatever built this signal built it inside a 1971 Fairchild Semiconductor processor housing and has been running it at 1,000 times the rated clock speed for 55 years. The silicon in that package is not doing what silicon does. I want to see what it looks like from the inside before the bit depth climbs any further. Sully nods. She is already pulling the fiber optic camera from the equipment locker. The endoscope is rated for internal inspection of sealed cavities, a 3 mm flexible cable, a 6-axis articulating tip, a high-resolution sensor at the end. They will thread it into the CLU housing through the ventilation port and look at the core of the machine that is encoding the surface of the moon in the fabric of this room. She stops with the cable in her hands. If the relay gap is a tuned gravitational aperture, she says slowly, and the CLU is the processor running the map, what is the CLU housing? She looks at the endoscope cable. We're threading a camera into a gravitational transmitter, into the aperture end. Thorne looks at the cable, at the CLU housing visible through the observation window, the sealed aluminum box at the heart of the chassis. Yes, he says. and we don't know what the field geometry looks like inside the housing. No. She looks at the cable for another second. Then she caps the connector end with the protective sleeve, picks up her stimulant can, and finishes it in 2 swallows. Then we go slow, she says. The gravity sensor marks its microfluctuation. 1.2 Hertz, 67 times per minute. The map of the moon rotates on the display behind them, 14 alignment lines in red marker. The signal doing exactly what it has been doing for 55 years. Exactly what it was designed to do, by something that understood gravitational physics that humanity would not formally describe for another 4 decades, inside a machine that human hands assembled in Worcester in 1971. The map updates. It has been waiting for someone to open the CLU housing since before Thorn was born. Chapter 6. The Corroded Bypass. Thorn has the laser aligned on the first corroded terminal at 0800 and the corrosion moves before he fires. Not much. 1 millimeter, maybe 2. A slow peripheral retreat of the dark oxidized crust away from the terminal post, as if the material sensed the targeting beam and is responding to it. He holds position. He watches. The crust stops moving. He does not fire. Sully, I see it. She is on the overhead camera, tight field on the terminal block. It moved when the alignment laser hit the surface. Not a thermal response. The alignment beam is 0.03 watts. Not enough to heat the substrate. It's a photonic response. She is already pulling up the UV spectrogram. Give me 20 seconds. He holds the laser off the terminal and waits. The crust is still. The 1.2 Hertz baseline moves through the floor. The corrosion is biometallic, Sully says. Her voice is flat and fast, the register she uses when she has found something she does not want to have found. UV return matches the coating on the bus bars. Same material, same photonic response signature. It's not corrosion. It's the same substance that was pulsing on the terminals in Mylar removal. It's been sitting on the relay connectors for 55 years, presenting as oxidized copper, and it is not oxidized copper. A pause. And it just tried to get away from your laser. Thorn looks at the terminal block through the magnification loop. 3 relay connectors on the bypass circuit. The connectors they need to bridge to force a direct data tap on the telemetry relay housing without routing through the primary crystalline bus. The bypass approach was Sully's idea from 2 days ago. If the primary bus is the signal's main transmission channel, a direct relay tap might reveal the signal's routing logic before it hits the bus. A read-only window into the relay stage. Clean, minimal, limited contact. The connectors are coated in the dark biometallic material. Thick at the edges of each post, thinner toward the center, following the contour of the terminal geometry with the conformal coverage he first documented on the bus bars in Chapter 2. The Mylar removal shift. Same silver dark surface color, same surface texture under the loop. He has been treating it as the same material in a different location. Infrastructure, like the bus bar coating. Part of the system. He has just learned it is not. It is not contamination. If the coating on the bus bars was infrastructure, part of the signal system, then this is too, he says. The bus bar coating is active. It pulses. It's in sync with the signal. She pulls up the terminal block spectrogram. The relay connector coating is quiescent. It's not pulsing. The UV response suggests it's in a different functional state. The bus bar material is transmitting, and the relay connector material is... She stops. Starts. It's blocking. The bus bar coating is an active component, and the relay connector coating is a seal. It's covering the bypass connectors because the bypass connectors are a path around the primary bus. Someone, something, doesn't want a direct tap on the telemetry relay. It's keeping the circuit closed. It's keeping us out of the circuit. There's a difference. She looks at the terminal block on the overhead feed. The primary bus wiring has been replaced with crystalline conductors. The relay connector bypass is still coated in a biometallic seal. The system has specific points it wants accessible and specific points it wants closed, and this is a closed point. Thorn sets the laser back on the targeting rest and picks up the long-wave UV wand. He runs a slow pass across the terminal block, giving the material time to respond. On the bus bars, the UV response is immediate and synchronized. The biometallic coating pulses in exact phase with the 1.2 Hz signal, bright and deliberate, a photonic emission that is clearly part of the signal's operating cycle. Active, transmitting. The relay connector coating responds differently, slower. The pulse it produces under UV is irregular, aperiodic, no synchrony with the baseline signal, and with each pass of the wand, the thicker sections of coating contract, not dramatically, fractions of a millimeter, visible only under the loop, pulling slightly inward, away from the UV source. The geometry of each retreat following the path that increases the material's distance from the light. It is not responding to the UV as a photonic stimulus. It is avoiding it. He passes the wand over the same section a third time and watches the contraction under the loop and uses the word he has been resisting since the Mylar removal. The word that the movement and the response and the directed retreat keep insisting on. It is behaving like tissue. He notes it in the shift log in those exact words, then puts the wand down and picks up the laser. When the laser bridges the gap, he says, the circuit completes. Whatever the biometallic seal was blocking, the direct telemetry relay tap, the signal will have a new path. I know. The signal has been adding capabilities with every access point we've opened. Probe contact added handshake response. Faraday cage added 42% amplitude. Mylar removal added 4 decibels. I know. She is pulling up the capture stack, getting every recorder live, checking timestamps. The bit depth is at 53. It's been climbing since the cage. If the bypass gives it a direct path to the telemetry relay, it will have access to the communications stack, the dish, the antenna array, the full transmission hardware. A fast breath. It will be able to aim. Thorne looks at the dish, at the communications antenna angled toward the ceiling, toward the roof, toward the lunar surface 238,000 miles away. The signal has been transmitting since the relay gap, through the gap, without the antenna, at whatever power a gravitational propagation without a tuned aperture can sustain. The relay circuit bypass would connect the signal directly to the communications hardware, to the antenna dish, to the transmission chain that was designed and optimized to send a signal to the moon. We fire the laser, he says. We fire the laser, she confirms. She is not arguing. This is the protocol. You do not stop at the obstacle. You document the obstacle and you breach it, because the data on the other side of the obstacle is the reason you are here. She is confirming because confirmation is the procedure. Air gap closed. All recorders live. Thermite circuit is armed and standing by at the CLU. On your mark. He marks. The precision laser fires a 300 millisecond pulse at 4 watts, bridging the gap between the first corroded terminal post and its connector contact across 2 millimeters of biometallic seal. The seal does not burn. It does not spark. It does not ablate or vaporize or char the way a passive material would under a 4-watt laser at this focal length. It does what living tissue does when you cut it. It bleeds. A thick silver, ferrofluidic substance wells up at the point of laser contact, not vapor, not ablation residue, a liquid, dense and coherent, emerging from the biometallic material as if the laser punctured a pressurized layer beneath the surface crust. The fluid moves laterally across the connector face with directed purpose, not pooling, not following gravity, moving away from the bridged point toward the edges of the terminal housing, the way blood moves away from an incision along the path of least surface tension. Thorne watches it under the loop, and his hands do not move and his expression does not change, and he writes in the shift log, seal material, liquefies on laser contact, ferrofluid behavior, directed lateral movement. He does not write the word that is sitting behind that sentence. He does not need to. The video record will show it. The fluid reaches the edge of the connector housing and does not stop. It is flowing toward the housing wall, climbing it in a thin silver film, moving away from the bridge terminal with a slowness that is not the slowness of surface tension and is not the slowness of viscosity. It is the slowness of something deciding where to go. It's retreating. Sully says. The seal it's contracting away from the bridge point. The laser is completing the circuit and the material is, Elias, the material is alive. It's pulling back like a scab retracting from a wound. Stay on the recorders. I'm on the recorders. I'm on the recorders. The UV response on the retreating material is going active. It's pulsing now. She stops. The bit depth jumped. It just jumped. It was 53 and it is now. A half-second of silence that, in Sully's register, is a long time. It's climbing fast, faster than it climbed after the cage. The direct relay path it's like opening a valve. The signal has a clean path to the communications stack and the ceiling monitors carry the baseline throb, and then the baseline throb changes. Not in frequency. The 1.2 Hz fundamental holds, metronomic, unchanged. The change is in the harmonics. The overtone series above the fundamental, the 2.4, 4.8, 9.6 Hz stack that has been present and stable since day one, shifts. The ratios change. The harmonic series reorganizes into a new configuration, the overtones moving to new frequency positions, the whole spectral stack reshuffling in under a second into an arrangement that Thorne has not seen in 4 days of monitoring this signal. The signal is reconfiguring. Sully. I hear it. I hear it. The harmonic stack is reorganizing. It's not noise. It's moving with. It's structured. She is typing and watching the spectrum and talking simultaneously, all three at different speeds. The new relay path gave it access to the transmission routing logic, and it's rebalancing the harmonic series around the new signal geometry. The overtones are moving to new positions. She pulls up the harmonic comparison, before and after. This is not signal degradation. This is tuning. It's tuning itself to the relay bypass. A pause that is too short to be comfortable. Elias, the dish is warm. How warm? 2 degrees above ambient. She reads it twice. The communications dish. It was ambient when I checked it at 0800, and it is now 2 degrees above ambient, and the current sensor on the antenna feed line is. Her voice goes very quiet. It's reading. The antenna feed line is drawing current. The dish is active. Thorne straightens and looks at the communications dish. 2 degrees of thermal differential is nothing in isolation. Within the noise floor of environmental causes, within calibration uncertainty, within a dozen innocent explanations. But the dish has returned ambient readings on every measurement since the rover arrived. Every reading for 4 days, not drifting, not fluctuating. Ambient, cold, dead, 2 degrees. The harmonic stack continues its reorganization on the spectrum display. The bit depth counter is at 61 and moving. The biometallic seal has retreated fully from the bridge terminal. The laser circuit is complete. The relay bypass is open. And the ferrofluidic material that was the seal has pooled at the edges of the connector housing in a thin silver film, no longer moving, holding position at the boundary of the bridged zone, waiting to see if the bridge holds. Second terminal, Thorne says. Elias. Second terminal. We breach all 3, or we learn nothing. He keeps his voice level. The first bridge showed us the seal behavior, the fluid mechanics, the harmonic reorganization. That's one data point. We need the full relay bypass open to understand what the signal does with access to the complete transmission chain. 1 bridge terminal gives it a partial path. 3 gives us the picture. She does not answer immediately. He can hear her running it. The risk calculus, the bit depth number, the dish temperature, the ferrofluid pooling at the connector edge. He can hear her arriving at the same place he arrived 30 seconds ago, which is that the protocol says you complete the procedure and the procedure requires all 3 terminals. Second terminal, she says. Mark when ready. He does not mark immediately. He looks at the dish. The thermal probe on the antenna mount is reading 2.4 degrees above ambient now. It has climbed by 0.4 of a degree in the 90 seconds since he bridged the first terminal. The rate of climb is not alarming. The fact that there is a rate of climb is. He checks the thermite circuit status on the CLU. Armed. Trigger in Sully's hand, right once tape in the recorder, air gap closed on every instrument. Protocol is satisfied. He aligns the laser on the second terminal post. The biometallic coating on it has not retreated. Only the first terminal's coating moved when the bridge fired. The second terminal is still sealed, the dark material sitting thick and undisturbed on the connector face, the ferrofluid from the first breach pooled at the housing edge 3 centimeters away. The signal is waiting for the second bridge. He can feel it in the floor the way he has felt it for 4 days, the 1.2 Hz pulse, the subsonic presence. But there is a quality to it now that he cannot log in instrument terms. A directionality. The same quality he felt in the Faraday cage, the focused pressure from the relay gap. The chassis is oriented toward the second terminal, toward the laser, toward him. He fires. The second seal bleeds silver. The ferrofluid wells, moves, retreats to the housing edge. The harmonic stack on the spectrum display shifts again. A second reorganization, faster than the first, the signal adapting to the new routing path in real time. The dish temperature jumps, not 0.2 of a degree, not 0.4. A full degree in under 3 seconds, and Sully is already reading it before he can ask. Dish is at 4 degrees above ambient, and it's not slowing. Third terminal, Thorne says. Elias, the dish is third terminal. A beat. 1 full 1.2 Hz cycle. Mark, she says. He fires the third bridge. The ferrofluid from all 3 terminals moves simultaneously. A coordinated retreat from all 3 breach points at once, all flowing toward the same corner of the connector housing, pooling together into a single silver mass that sits dense and still at the boundary of the bypassed circuit. The biometallic seal has withdrawn from every connector in the bypass. The relay path is fully open. The signal has access to the full communications stack, relay logic, antenna routing, transmission hardware, the dish. The harmonic reorganization completes. The spectrum display settles into its new configuration. The same fundamental, a new overtone series. The signal's full operational geometry now expressed through the communications hardware it was built to use. The dish temperature is 6 degrees above ambient, and the current sensor on the antenna feed line is reading 48 milliamps and climbing. The signal is aiming. Thorne looks at the communications dish, at the antenna angled toward the roof, at the 48 milliamps flowing through a circuit that was reading 0 4 minutes ago. What is the transmission target? He says. Sully is already running the direction-finding stack. She runs it for 11 seconds. She turns around. Hadley-Apennine, she says. Direct line of sight. It's not pinging a relay. It's aimed at the surface. The dish is warm. The signal is transmitting. And whatever is at the Hadley-Apennine site has just received a message that the bypass is open. Chapter 7. The Logic Trap. The logic gates in the CLU are moving, and Thorne has been watching them move for 4 minutes before he can bring himself to log it. Not metaphorically, not in the data. The physical gates, the Fairchild Semiconductor silicon substrate inside the central logic unit housing, the microscopic switching elements etched into the chip in 1971 at a gate density of approximately 2,000 transistors per square millimeter, are physically relocating on the die surface. The scanning electron microscope feed on Thorne's primary display is running at 10-second intervals, and between each frame the gate geometry changes. Individual transistor structures migrating laterally across the substrate by distances measurable in nanometers. The die is rearranging itself. He logs it. He logs it the way he has been logging everything for 7 days. Flat, specific, instrument data first. CLU die substrate. Gate migration confirmed. 10-second interval imaging. Lateral displacement. Measurable. Mechanism. Unknown. He does not write what is sitting behind those sentences. He needs her to look at the same feed and arrive at the same word on her own. He needs it to be in her log independently, because if she sees it too, then it is real in a way that his own observation cannot make it real alone. 20 years of this work. He has always been able to call a colleague and have them look at the reading and confirm the artifact, confirm the coupling artifact, confirm the measurement error. He needs her to look at these gates and confirm the artifact. He already knows there is no artifact. He calls Sully in from the signal lab anyway. She arrives in 90 seconds, looks at the SEM feed, looks at the displacement overlay he has built frame by frame from the last 20 minutes of imaging, and says, "How long?" 22 minutes of confirmed movement. Possibly longer. I've had the SEM on since 0700 and I didn't pull the frame comparison until 818. She sits down at the analysis bench without taking her eyes off the overlay. The gates are migrating toward the shadow logic regions. "Show me." She pulls up the die map they built during yesterday's CLU disassembly, the full schematic of the substrate, annotated with every standard Fairchild circuit element, and the anomalous elements flagged in red. The standard elements, gate arrays, interconnect buses, the navigation processing logic, the telemetry multiplexer, all of it present and documented in the original Boeing design spec. All of it where the spec says it should be. All of it functional as drawn. Thorne verified every standard element against the schematic and found no deviations. Then he ran the inverse analysis, looked at the silicon that is not accounted for in the spec, looked at the gate structures and interconnects that exist on the physical die but have no corresponding entry in any Boeing or Fairchild document in the facility's archive. There are a lot of them. The shadow logic regions, extra processing paths etched into the silicon at a scale smaller than the standard elements, present in the spaces between the documented architecture, using the interstices of the original design as real estate for a parallel processing network that the original designers either did not build or did not know was there. Extra gates, extra interconnects, routing paths that serve no function in the navigation and telemetry spec because they are not serving the navigation and telemetry spec. They are serving something else. Under the SEM at high magnification, the shadow logic elements have a different crystallographic texture than the surrounding standard silicon, a finer, more regular lattice structure, the kind of atomic level organization that does not happen by accident and does not happen in a 1971 semiconductor fab. They found them yesterday. What Thorne is looking at this morning is not what they found yesterday. 30% 2 days ago. Thorne looks at the current die map. The shadow logic fraction is larger. It grew, he says. The gate migration is building the shadow logic network. The standard circuit elements are relocating to create more shadow logic pathways. She is pulling comparison frames fast, overlaying them. The die is restructuring itself to expand the anomalous processing architecture. The Fairchild original design is being consumed, incorporated. The standard gates are being assimilated into the shadow logic network. She looks at the current die map. Elias, the shadow logic fraction was 31% when we mapped it at 0900 yesterday. It is currently, she runs the boundary analysis, 47%. In 22 hours, the shadow logic network has grown by 16 percentage points. It is eating the original chip. The SM cycles its 10-second interval. The feed updates. Thorne watches the new frame render and finds 3 gate structures that were in one position 10 seconds ago and are now in a slightly different position. Their migration path clearly oriented toward the nearest shadow logic interconnect, moving toward the network, being pulled. He picks up the thermal probe and holds it 2 centimeters above the CLU housing. He does this without announcing it because Sully is running the migration rate data and does not need the narration. He does it because the thermal map has been the most reliable indicator of the shadow logic network's operational state. More reliable than the bit depth counter, more reliable than the SEM gate migration rate, because the thermal draw is a direct measure of power consumption. And power consumption is the most honest number a processor produces. It cannot be encrypted. It cannot be routed. It just draws heat from its environment, and the environment records the loss. He checks the reading. 41 degrees Kelvin. He holds the probe at the same distance and checks it 3 times. The number does not change. The housing is at 41 degrees Kelvin, minus 232 degrees Celsius, 32 degrees above absolute zero, in a room maintained at 68 degrees Fahrenheit by a climate control system that has been running at full capacity since the Faraday cage session without recovering the temperature delta. The room is losing. The cold spot wins every cycle. 2 days ago, the CLU housing read 60 degrees Kelvin. In 48 hours, the housing has dropped 19 Kelvin. The shadow logic network is consuming more thermal energy as it grows, pulling harder against the room's heat budget. The processing load scaling with the network's expansion. His breath fogs above the probe. He watches the condensation form and drift and thinks about the scale of computation that requires minus 232 degrees Celsius worth of thermal extraction from a sealed aluminum box in a temperature-controlled clean room. And the number is not a number his training has a framework for. Clock speed, he says. She pulls up the clock diagnostics she ran at 0730. The CLU's original Fairchild architecture was designed to run at approximately 2 MHz, a standard clock rate for 1971 aerospace computing, adequate for the navigation and telemetry functions the rover was built to perform. She ran the clock diagnostic using a non-contact electromagnetic probe, and the reading it returned required 3 verification passes before she wrote it in the log. 2.1 terahertz, she says. Effective clock rate. The shadow logic network is processing at 2.1 terahertz using a 1971 silicon substrate. That's not possible. It's running at 1,000,000 times the design clock speed using transistors that cannot physically switch at terahertz rates, except these can, because they are not the original transistors anymore. She pulls the conductivity data, fast. The crystal lattice has been restructured. Doping profile, band gap, carrier mobility, all of it modified at the atomic level inside a sealed housing without disassembly. 0 resistive loss. Room temperature superconducting silicon. No human fabrication process in 1971, or now, can do this to a sealed chip. You cannot atomic layer deposit inside a closed package. You cannot ion implant through an aluminum lid. She looks up. The shadow logic was not manufactured in a fab. It grew inside the housing. Over 54 years, using the silicon substrate we gave it as raw material, restructuring it atom by atom into something we could not have built with our best current equipment. A pause. It is still growing. Right now, in a box on that bench. She looks at the CLU. We have been calling it the ghost. We have been treating that as a metaphor. She does not finish the sentence. She does not need to. The CLU housing hums below audible, a subsonic vibration Thorne can feel through the bench surface when he leans close. The chip inside that housing is running 2.1 trillion switching cycles per second, drawing thermal energy from the room in measurable quantities, migrating its own gate architecture toward greater efficiency in real time. And it has been doing all of this in a sealed aluminum box in a NASA warehouse while successive engineers checked the exterior, noted no anomalies, and signed off. It's like finding a supercomputer hidden inside an abacus, he says. It is a supercomputer hidden inside an abacus. She is already at the migration rate data, pulling projections. And it's not done. The 31% from yesterday was not a ceiling. It was Tuesday. It's still going. She runs the projection and reads the output and does not read it aloud immediately. She turns it toward him. He looks at the number. How long until the shadow logic network consumes the entire die? He says. 61 hours at current rate. She pulls her hand back from the display. In 61 hours, the original Fairchild Semiconductor chip is gone, completely incorporated. The CLU housing will contain a room temperature superconducting terahertz processor built from restructured NASA silicon, and there will be no external indication that anything changed, because the housing is the same housing and the package dimensions are the same, and the connector pinout is the same. She looks at the housing. It will look exactly like a 1971 navigation computer from the outside. 61 hours, 2.5 days. The original Fairchild Semiconductor silicon that Boeing installed in this housing in 1971. The silicon that navigated 2 men across the lunar surface, that processed telemetry data from the 28-volt bus, that was designed and manufactured and tested and certified and launched on a Saturn V rocket and driven across the moon and brought home and stored for 54 years, will be completely gone, fully incorporated, replaced at the molecular level by a room temperature superconducting processor, running at 1,000,000 times the design clock speed, built from the same physical material, occupying the same housing, undetectable from the outside. The thing consuming the Fairchild chip did not bring its own hardware. It used ours. It moved in, found the substrate, and is building what it needs out of what was already there. The CLU housing ticks in the subsonic range. Thorne's breath fogs 2 centimeters above the housing surface. The cold spot deep and stable. The room's ambient heat draining toward this point at a rate his FLIR data says has been consistent for 3 days. The bypass opened the communication stack, Thorne says. We gave it the dish. Transmitting and receiving. Her voice is flat. Direction finding confirmed bidirectional traffic on the dish at 0600 this morning. Not broadcast, not ping and echo. Structured bidirectional data exchange. Something at Hadley-Apennine is sending data back through the dish, and the shadow logic network is processing the return feed. She looks at the bit depth counter, 74, and holding. The processor growth and the incoming data are linked. The shadow logic network is expanding to handle the inbound data load. The more data comes in from the moon, the more processor it builds to process it. Thorne looks at the SEM feed. At the gates moving in their 10-second intervals, the die consuming itself in service of a network that is growing to accommodate a conversation with the moon. The thing at Hadley-Apennine is sending data back through the dish, and the shadow logic network is building itself bigger to receive it. At 2.1 terahertz and climbing. He does not know what the data contains. He does not know what it is building toward. He knows the gate migration has 61 hours of runway at current rate, and he knows the bit depth counter is at 74, and he knows the CLU housing is at 41 degrees Kelvin, and the dish is transmitting and receiving, and the room is getting colder, and none of his containment measures are slowing any of it. We need the endoscope, he says. The shadow logic architecture on the die surface is the outside. I need to see what is at the center of the CLU housing, before the 61 hours runs. Sully looks at the SEM feed, at the gates migrating toward the network, at the cold locus in the thermal map, the floor of the temperature gradient, the coldest point in an already cold room. The cold spot is the center, she says. Yes. We're going to thread a camera into the coldest point in the room and look at what's making it cold. Yes. She picks up the endoscope cable from the equipment locker, still capped, still sitting where she left it 2 days ago when she identified the aperture risk and they both decided to wait. She turns it over in her hands once. The 3mm flexible fiber, the articulating tip, the high-resolution sensor. The migration rate increases when we open the housing port, she says. The cold spot is thermally sealed by the housing lid. We breach the lid, the thermal gradient equalizes, the processing load drops, or the load spikes because the boundary condition changed and the network compensates. She looks at the housing. I don't know which. Neither do I. And we have 61 hours before the question becomes academic because the original chip is gone, and we have no reference state left to compare. Yes. She looks at the endoscope cable, at the housing, at the SEM feed where 3 more gates have just moved in the 10-second interval. If the cold spot at the center is the power source, she says, and she has been working toward this, and Thorne has been working toward it too, the inference that keeps forming at the edge of the data. Then what we are about to point a camera at is the thing that is eating the heat in this room to stay online. Yes, he says. She uncaps the connector end. The CLU housing is at 41 degrees Kelvin and dropping. The shadow logic network is processing bidirectional traffic with the moon at 2.1 terahertz and climbing. The dish is warm, the gates are migrating, the bit depth counter is at 74, and the center of the housing has never been opened and has been cold since before anyone in this facility knew it existed. In the SEM feed, 3 more gates move. They are all moving toward the center, toward whatever is making it cold. Chapter 8. The Thermal Anomaly. The FLIR returns 20 degrees Kelvin on the CLU housing, and Thorne has to recalibrate the camera because the reading is below the instrument's rated lower threshold. He recalibrates. He runs the calibration sequence against the reference target. a precision blackbody source at a certified temperature, and the camera performs correctly against the reference. He points it back at the CLU housing. 20 degrees Kelvin, not 41. Not the 38 he logged before the end of yesterday's shift. 20. The housing has dropped 21 Kelvin overnight with no change in facility climate control, no change in instrument contact, no change in anything except that the shadow logic network inside that housing has had another 8 hours to grow, and the gate migration continues, and the cold spot is no longer a spot. He walks the FLIR camera slowly across the chassis, building the thermal map from the CLU housing outward. The housing itself is the floor, 20 degrees Kelvin, a region of near absolute zero that the camera renders in deep blue, the coldest color in the display palette, a color that does not belong in a temperature-controlled clean room in Worcester in November. From the housing, the gradient climbs outward through the aluminum frame of the chassis, 30 degrees at the spar nearest the CLU, 45 at the instrument panel mounts, 62 at the front axle support. The platform beneath the rover is reading 51 degrees Kelvin at the contact points. The cold is conducting through the mounting feet into the steel, into the facility floor, into the building. He walks the camera to the far wall. He does not walk quickly. His fingers are stiff inside the nitrile gloves, not painfully, just reduced dexterity, the early stage effect of sustained cold exposure on fine motor control. The FLIR reads 42 degrees Kelvin on the copper mesh at the closest panel. He steps back and sweeps the camera up to the ceiling. The air filtration housing at the center reads 51 degrees Kelvin, the ducts running outward to the wall vents at 58. The vents themselves, where the heated air enters the room, read 64 degrees Kelvin on the duct face and 49 on the grill surface, a centimeter from the room interior. The heated air is losing 41 degrees Kelvin in transit from the duct face to the room. The building is losing heat to this machine, and the radius of the loss is the entire clean room, and the clean room's HVAC system is fighting a thermal gradient it cannot close. Sully comes in at 0720. She has her stimulant can and her probe kit, and she stops 3 steps inside the door, because the cold hits her the same way it hits everything that enters this room now. Immediately, fully, without buildup. She exhales and watches her breath fog and does not say anything about it. She crosses to the FLIR display and reads it before she takes her coat off. She puts the stimulant can down without opening it. 20, she says. 20 on the housing, 42 on the wall mesh. Yesterday the wall mesh was ambient. She is at her station, pulling the overnight data stack, scanning it fast. Bit depth, dish current, harmonic profile, gate migration rate. The cold boundary expanded 14 meters overnight. The entire room is inside the thermal draw radius. She pulls up the facility power log. Elias. The building's HVAC has been running at maximum capacity since 0200. It's been trying to compensate for the heat loss and it cannot keep up. She looks at the power consumption graph. The HVAC draw climbing steadily from midnight, peaking at full rated output at 0214 and holding there. The system working at maximum to maintain a room temperature that is dropping anyway, because the machine in the center of the room is consuming thermal energy faster than the building can replace it. It's eating the heat in the room to stay online. Thorne sets the FLIR camera on the bench and looks at the rover. At the CLU housing, cold and dark in the FLIR image, a region of near absolute zero sitting on a platform in a clean room in a university-adjacent research facility in New England. At the thermal gradient radiating outward from it through the chassis, through the platform, through the floor and walls, the cold propagating spherically through every thermally conductive material in the room. His breath fogs. It has been fogging since he entered the building this morning. Not in the corridor, not in the equipment room, not at his desk in the administrative section. In the clean room. The moment he came through the inner door, the condensation started, and it has been present for 40 minutes now. Every exhaled breath producing a small, visible cloud that drifts upward and disperses, and he has been noting it as a data point and not saying it aloud, because saying it aloud would require discussing what it means to work in a room that is thermally hostile to human occupancy. The room is 33 degrees Fahrenheit at ambient. The climate system says 68. The climate system is losing. FLIR survey of the chassis cavity, Thorne says. I need the thermal profile inside the frame, underneath the instrument panel, the CLU housing interior, if the camera resolves through the aluminum, the bus housing. Sully is already pulling the long-wave infrared lens from the equipment locker. Higher thermal sensitivity, better resolution at the temperatures they are dealing with now. She mounts it on the FLIR body and brings the camera to the chassis. She runs it slowly along the underside of the instrument panel, the camera angled upward into the chassis cavity. The display builds the image from the bottom up. The CLU housing interior does not resolve. The aluminum lid blocks the long-wave return. The camera cannot see through the housing. But the chassis cavity adjacent to the housing tells the story. The aluminum structural members nearest the CLU are at 18 degrees Kelvin. The internal wiring harness, the crystalline bus conductors, glowing their faint glow in visible light, is at 22 degrees Kelvin. The Fairchild 709 operational amplifier packages bolted to the instrument panel backing plate are at 15 degrees Kelvin. The op-amps are colder than the housing. The op-amps are downstream of the CLU in the processing chain, Thorne says. The shadow logic network in the CLU is pulling thermal energy from every component in the processing path. Not just the housing. Everything electrically connected to the shadow logic architecture is a heat source it can draw from. Everything electrically connected. Sully pulls the camera back and holds it. The crystalline bus conductors connect the CLU to the telemetry relay to the antenna stack. The relay bypass connects to the communications hardware. The dish is connected to the bus. She looks at the dish. She points the camera at the dish. The communications dish is at 28 degrees Kelvin. The dish that was at ambient temperature 6 days ago. The dish that read 2 degrees above ambient when the relay bypass opened and 48 milliamps started flowing through the antenna feed. The dish has been drawing current for 36 hours, and the shadow logic network has been drawing the dish's thermal energy for at least that long, and it is now at 28 degrees Kelvin, and the antenna elements on its face are at 24. The entire transmission chain is a heat sink, Sully says. Flat, fast. Not panicking. She has passed the panic register, into the place beyond it where the data is happening faster than the emotional response, and she is just narrating what the instruments say. The shadow logic network treats every connected component as a thermal reservoir. CLU, op-amps, bus conductors, relay housing, antenna stack. It's drawing from all of them simultaneously. The processing load isn't localized to the chip. It's distributed across the full electrical topology of this rover, and it is eating every joule of thermal energy available in every component it can reach through a conductor. She sets the camera down. Elias. Her voice drops a register, the specific quiet she uses when she needs him to actually hear the next thing. The cold is in the transmission chain. The cold is in the antenna feed line. The cold is in the dish. She looks at the dish, at its 28 degree Kelvin surface, at the antenna elements at 24, at the feed horn at the focal point that is 17 degrees Kelvin, colder than the CLU housing, the coldest point on the entire chassis. The coldest point on this rover is not the processor, it's the transmitter. She looks at him. The cold is aimed at the moon. The HVAC runs at maximum. The room temperature is 33 Fahrenheit and falling. Thorne's breath fogs in a continuous stream now, not discrete clouds. The exhaled moisture is condensing before it disperses. The air in the room too cold to absorb it. The ambient temperature below the dew point of human exhalation. He checks the wrist monitor he has been wearing since day 3. He has been checking it every 20 minutes, logging the readings, watching the number hold at his baseline of 98.6 with minor fluctuations throughout the previous shifts. Baseline, baseline, baseline. Core temperature, 97.6 Fahrenheit. 1 degree of drift in 42 minutes. The room is pulling his body heat the same way it is pulling the buildings. Not fast, not dangerously fast, not yet. But measurably and in one direction, and without any countervailing mechanism, because the thing running in the CLU housing does not have a floor temperature, and does not have a satiation point, and will continue pulling from every thermal reservoir in its radius until the reservoir is exhausted, or the system is stopped. He looks at Sully. She has not checked her own wrist monitor. She is looking at the FLIR display. Work rotation, he says. 40-minute maximum in the clean room. Body temperature mandatory on entry and exit. Anyone below 97 on exit goes to the medical station before the next rotation. He waits until she looks at him. That is not optional. I know. She checks her monitor. She reads the number and does not say it and logs it on her tablet. She is looking at the FLIR display. At the 20 degrees Kelvin on the CLU housing. At the thermal map of a chassis that is cold from end to end. The entire machine a distribution network for a heat sink that has no bottom temperature he has yet been able to locate. The power source question, she says. We've been asking where the signal gets its power. Zero current in the wires, no battery, no capacitor, no external supply. She looks at the thermal map. This is the answer. It's not generating power from nothing. It's not drawing from the vacuum or the zero-point field or any of the things we were speculating about at the start of this. She looks at him. It's consuming it from the environment. It's eating the heat in the room to stay online. Thorne looks at the thermal map. At the building's HVAC running at maximum capacity and losing ground. At the op-amps at 15 degrees Kelvin and the dish at 28 and the chassis at 30 degrees on the warm end and the CLU housing at 20 and dropping. The machine is not generating energy. It never was. There is no zero-point field draw, no vacuum energy tap, no exotic physics. The answer is simpler and in some ways worse. It is harvesting energy. Thermal energy. From everything warm enough to give it. From the room, from the building's climate system, from the thermal output of every warm object within the cold gradient's radius. It does not have a power supply in the classical sense. It has a demand function. It calculates the processing load required. It calculates the thermal energy that load requires, and it draws that energy from its environment with the indifference of a drain in a bathtub. The environment does not get a vote. The drain does not negotiate. It takes what it needs and leaves the remainder, and the remainder is getting smaller. The building will lose the equilibrium calculation eventually. So will they, if they stay in this room long enough in the wrong rotation schedule. He looks at his breath fogging in the heated air that is not, in any functional sense, heated anymore. And he thinks about the two men who drove this rover across the lunar surface in July of 1971, and whether the thermal draw was active then, and whether the moon was warmer near the Hadley-Apennine site after they left, and whether anyone measured it. Get the endoscope prepped for tomorrow, he says. Full insertion protocol. We go into the CLU housing at 0700. She nods and does not say what both of them are thinking, which is that the housing is at 20 degrees Kelvin and the endoscope fiber optic cable has a rated minimum operating temperature of 230 degrees Kelvin, and threading it into the CLU housing will destroy the sensor within seconds of contact with the internal thermal environment. They will need a different instrument, or they will need to go in knowing the instrument will not come back out intact, and they will need to extract their data from the sensor before it fails, and they will need to work fast because at 20 degrees Kelvin the fiber optic cable will become brittle within seconds of contact, and the sensor housing will fail within 10. He thinks about what is inside the housing, about the center of the cold gradient, about the SEM feed showing every gate migrating toward the center of the die, about what sits at the convergence point of a processing network that is consuming thermal energy from a radius that now includes the entire building's climate system, and has been doing so since before he logged the first anomaly. He has been working toward this for 8 days. Every measurement, every layer stripped away, every probe contact and laser bridge and FLIR scan has been a step toward the center of the CLU housing, toward whatever is making it cold. He is 8 hours and 1 endoscope insertion away from knowing what it is. He adds the instrument loss to the planning log. He adds it flat, the way he adds everything. He notes the sensor failure timeline at 20 Kelvin. He notes the data extraction window. He notes that a second sensor will be needed on standby. He draws a line under it. He checks his wrist monitor again, 97.4. He has been in the room for 44 minutes, 2 minutes over protocol. Chapter 9. The Obsidian Shard. The fiber optic camera clears the CLU housing port at 0714, and the feed is not what Thorne expected. and he has spent 4 days building very careful expectations. He expected darkness. The housing interior is unlit. No power source connected to the internal illumination circuit, the original Boeing indicator LEDs long since dead. So he brought the endoscope's integrated illumination array. 4 micro LEDs at the tip, 12 lumens of white light in a tight forward-facing cone. He expected to need them. He expected to be working against low light conditions, straining to read the detail in a dim interior. The interior is dark. But the dark is wrong. The illumination array is functioning. The diagnostic channel confirms all 4 micro LEDs are firing at rated output, 12 lumens forward, the kind of light that would wash out a human retina at this distance. At this range in a sealed enclosure, 12 lumens of white light should produce a near-blinding return from any reflective surface. The original Fairchild silicon has a polished surface. The copper terminal posts on the motherboard connectors are reflective. The aluminum walls of the housing are reflective. The feed should be bright. The feed is dark. Thorne advances the cable. The illumination array continues firing. The feed continues returning near black. Not sensor failure. The diagnostic confirms the sensor is live and receiving, but receiving almost nothing, as if the surfaces in the housing are consuming the light rather than reflecting it. He checks the LED current draw, all 4 micro LEDs pulling rated amperage. The light is going in. The light is not coming back. He leans closer to the monitor, a reflex that accomplishes nothing. The display resolution is fixed. The sensor data is what it is. Leaning in does not help. He does it anyway. Something in there is absorbing, he says. The floor and walls are normal. I've got aluminum reflections on both sides. Sully is reading the sensor return data raw, column by column, parsing what the rendered image cannot show her. But there's a central mass that is returning essentially zero. Not low, zero. Every photon the array is putting into the central volume is being absorbed and not re-emitted. The center of that housing is a light sink. A pause. Elias? The thermal draw from the CLU housing has been the coldest point in the room for 3 days. And the light absorption is also centered in the CLU housing. Same location, same geometry. She does not complete the inference out loud. She does not need to. He advances the cable toward the center mass. The shard comes into focus gradually, the way a dark object in a lit space resolves as you move toward it. Not by getting brighter, but by the contrast between its absence and the reflective aluminum wall behind it. Thorne's first impression is of a shadow that has no light source to cast it, a region where the housing interior simply stops returning information. Then the edges resolve. It is black. Not dark gray, not the matte black of a painted surface or an anodized component. A black that is qualitatively different from darkness, the difference between a room with the lights off and a surface that refuses to acknowledge that there is light. The illumination array is putting 12 lumens into this object at point-blank range, and the object is giving none of it back. Thorne has never seen a material with this albedo outside of laboratory-engineered Vantablack samples, and this is not a laboratory-engineered material. It is jagged. Not manufactured jagged, irregular, crystalline, each face meeting the next at an acute angle without the precision of any fabrication process Thorne has encountered in 20 years of working with aerospace hardware. The profile of something that formed rather than was made. The edges are sharp, sharper than they should be for something that has been inside a sealed housing for 55 years. Sharp the way freshly cleaved crystal is sharp, as if the formation process was recent. The mass of it is approximately the size of a large fist. It is seated at the center of the CLU motherboard, and it is not held there by gravity or by mounting hardware or by any fastener in the Boeing parts catalog. It is held there by roots, not a metaphor, literal structural projections extending from the base and sides of the shard downward and outward into the motherboard, penetrating the Fairchild silicon surface at dozens of contact points. The shard integrated into the original NASA circuitry, the way a mineral deposit integrates into host rock, completely, irreversibly, at the level where the material boundaries have ceased to exist as separate things and become one continuous structure. I've got it, Thorne says. I see it. Sully's voice is flat. She is looking at the feed. The geometry is... It's not any mineral I have reference data for. The crystallographic profile of those edges doesn't match anything in the geology database. Not quartz, not obsidian, not any silicate or carbonate structure. It's its own thing. She pauses. It's beautiful, she says, and then seems to hear herself say it and goes quiet. And Thorn does not correct her because it is, and that is one of the things about it that is most difficult to reconcile with everything else it is. He advances the cable to maximum insertion depth, bringing the tip as close to the shard as the housing geometry allows. At this range, the surface texture resolves. The faces of the shard, which looked featureless at distance, have structure at close range. A microtopography of intersecting planes at scales below a millimeter. The surface fractal in its complexity, each face subdivided into smaller faces, subdivided into smaller faces, the geometry repeating at decreasing scale the way crystal lattices repeat, except that this repetition has no floor, no minimum scale at which the faces become flat. The endoscope camera is at its maximum resolution, and the surface detail at the pixel boundary is still structured. The structure goes deeper than the sensor can follow. Thorn looks at the feed and has the unsettling impression that if he advanced the camera further, if he could advance it past the surface and into the material itself, the geometry would continue. Smaller faces, smaller angles, structure all the way down, the same pattern at every scale. A form that carries its own design principle into dimensions below visibility. He does not advance the camera. He holds it at the current depth and takes the measurement record and moves on. The shard is vibrating. He cannot see the vibration. The frequency is too high, the amplitude too small. What he can see is the blur. The endoscope camera captures images at 30 frames per second, and at 30 frames per second, the shard's edges are not sharp. They are smeared. A motion blur artifact at the boundary of every face, the edges of the shard occupying a range of positions, rather than a single position in each frame. The blur band narrow but unmistakable. The visual signature of an object oscillating faster than the camera can resolve. It's vibrating, Sully says. She is watching the edge blur on the feed. The blur width corresponds to a frequency in the... She runs the calculation. High kilohertz range, minimum estimate, possibly megahertz. The camera can't resolve the actual frequency, only the lower bound. She looks at the spectral data running alongside the video feed, but the signal is at 1.2 hertz, the gravitational carrier, the chassis throb. It's all 1.2 hertz. She is quiet for a moment. The vibration we're seeing in the blur is a higher harmonic of the fundamental. The shard is vibrating at a resonant multiple of the signal's base frequency. It's the source and the resonator simultaneously. Thorn holds the cable steady and looks at the shard, at its roots in the motherboard, roots he can now see clearly at this range, the projections extending from the shard's base into the Fairchild silicon at contact points that correspond, he is certain, to the shadow logic gate locations they mapped on the SEM. The shadow logic network is not etched alongside the shard. The shadow logic network is the shard's root system. Every anomalous processing path they found in the chip is a root. The Fairchild Semiconductor navigation computer that Boeing installed in this housing in 1971 is not the processor in this system. It never was. It is the substrate, the growth medium. The silicon that the shard's roots penetrated when the rover touched the lunar surface and whatever was there began the process of integration. The Fairchild chip did not run the rover's navigation. The shard ran it through the roots, through the shadow logic gates that are its extended nervous system, through 55 years of slow integration that is still ongoing, is ongoing right now. The SM data from yesterday showing the migration continuing toward more root contact points, the shard still extending its reach through the original chip millimeter by millimeter. This is not a component of the rover's systems. This is the pilot. The roots correspond to every shadow logic gate location, Thorn says. Everyone, Sully confirms. She has the overlay running, the root projection map from the endoscope feed aligned against the SEM shadow logic distribution map. The correspondence is exact. The gate migration on the SEM, the molecular restructuring of the silicon, the terahertz clock rate. All of it is the shard extending its root structure through the original chip. She runs the structural analysis. The Fairchild substrate is the root system's medium. The shadow logic gates are the contact points. The root network is what the shard uses to process, to transmit, to run the gravitational map, to maintain the dish connection. She pulls up the full system diagram, every component they have mapped over 9 days, the crystalline bus conductors and the UV reactive coating and the relay gap and the communications stack, all of it connected to all of it. Elias, the shard is not running the rover's systems. The shard is the rover's systems. Every piece of this we've been investigating, the signal, the map, the bypass, the dish transmission. It's all this object. All of it is coming from here. This one thing, the size of a fist, sitting in a housing in a NASA computer, connected to everything through roots in 50-year-old silicon. The feed shows the shard in its housing, jagged black blurred at every edge, rooted into the motherboard of a machine that went to the moon. Silent and still except for the vibration that the camera cannot fully capture, the resonant oscillation at some high harmonic of 1.2 hertz that has been running in this housing since before Thorn was born. He checks the thermal probe reading on the housing exterior, 20 degrees Kelvin. The shard is the cold source. The shard is the processor. The shard is drawing the thermal energy from the room to run the calculations that sustain the gravitational map and the dish transmission and the shadow logic network and the ongoing root extension into the Fairchild substrate. The shard is the system. It has been the system since the moment the rover's wheels touched the regolith at Hadley-Apennine on July 31, 1971, and whatever signal it received from the surface completed its initialization sequence and it began to run. 2 men drove across the surface. They collected samples and deployed instruments and took photographs and drove back to the lander. They never knew what was running beneath them in the CLU housing. The navigation computer gave them coordinates. The telemetry system reported their vitals to Houston. The rover did everything it was designed to do, and simultaneously, without interrupting any of those functions, the shard ran its own program through its root network in the same housing, collecting its own data, building its own map, maintaining its own connection with whatever had been waiting at Hadley-Apennine since before the first hominid stood upright on another continent. The shard is the true pilot of the rover, Thorn says. Sully does not respond immediately. She is looking at the feed, at the blurred edges of the shard, the roots, the black surface that will not give back the light they are shining on it. The true pilot, she says. Yes. The room is cold. The chassis throbs at 1.2 hertz. The feed shows the shard in its housing, and the shard does not look back. And it does not need to, and it never needed to, because looking was never the point. Being there was the point. Having roots in everything was the point. The bit depth counter is at 93 and the shadow logic gates are still migrating and the dish is still transmitting to the moon. And whatever is at Hadley-Apennine has been receiving reports from this shard since before anyone in this building was born. And the shard has 44 hours left before its roots reach the last unintegrated gate in the Fairchild substrate. And when that happens, every transistor in the original chip will be part of the root network. Thorn does not know what the shard does when the integration is complete. He looks at the bit depth counter, 93. It has been climbing since the bypass opened, since the Faraday cage, since the first probe contact, 1 increment at a time, and the shadow logic gate migration rate has been the mechanism, and the mechanism is now visible and documented and understood, and none of that makes the counter stop. 44 hours until full integration. He pulls the endoscope cable slowly from the housing. The tip emerges clean, exactly as it went in. The housing port sits open and dark in the chassis face, and from somewhere in the depth of it the 1.2 hertz vibration continues, patient and exact, the same pulse it has maintained since 1971, neither faster nor slower for having been observed. Not responsive to observation, not altered by contact. A system that does not vary because it does not need to vary, because it was designed, grown, to run at this rate in this medium for this duration, and the duration is not yet complete. He caps the endoscope port with the housing blank. His breath fogs above the chassis surface. He reaches for the shift log. He writes, shard confirmed. Roots, full shadow logic correspondence. Vibration, high harmonic of fundamental. Assessment, primary system component. Origin, pre-launch. He draws a line under it. He does not draw a box. The data is not an action item. The data is the situation, and the situation does not fit inside a box, and the shift log is not large enough for what comes next. 44 hours. The bit depth counter ticks. 94. Chapter 10. The Bit-Decompressor. The vocoder outputs a heartbeat, and Sully knocks her stimulant can off the bench. It hits the floor and rolls, and neither of them moves to pick it up. They are both looking at the waveform display. The output is clean. Not noise, not artifact, not the kind of distorted muddy signal you get when you push a 1971 audio codec beyond its design parameters. Clean, structured. A rhythmic compression wave in the low-frequency audio range, the unmistakable acoustic signature of a cardiovascular pump in regular operation, and the rate is 72 beats per minute, and it has been playing for 11 seconds now without varying by a single beat. That's a heartbeat, Sully says. Yes. From the signal. The vocoder is decoding the 1.2 Hz pulse through the Apollo-era audio processing chain. That's the output. The 1.2 Hz pulse, the baseline signal we've been reading for 10 days, decoded through a 1971 vocoder, outputs a human heartbeat. Yes. She picks up a stylus from the bench and does not use it for anything. She holds it. Whose? Before Thorne answers, he needs to know whose, and to know whose he needs the biometric comparison, and to run the comparison he needs the reference data. The facility's archive contains the digitized NASA medical records from the Apollo program, the complete physiological telemetry that Mission Control received from every crewed lunar mission, archived continuously from crew ingress through surface operations through splashdown, heart rate, respiration, blood pressure, core temperature, the full biological data stream transmitted from the biomed harnesses the astronauts wore under their pressure suits, collected by the telemetry systems on the landers and rovers, and relayed to Houston and logged and stored in a federal archive that nobody has accessed for routine purposes in 15 years. He pulled the Apollo 15 records 2 days ago as a precautionary research step. He did not know then that he would need them this morning. He has them loaded. He runs the comparison. The vocoder output matches the Apollo 15 crew biometric records at a correlation coefficient that the software rounds to 1.000 before he can stop it from rounding. Dave Scott, he says, Mission Commander, Apollo 15. This is his cardiac signature from the 1971 mission telemetry. Sully does not say anything. But he's alive, Thorne says. He's 93 years old. He gave an interview last year. He looks at the waveform. At the clean, steady 72 beat per minute trace coming out of a vocoder that is decoding a signal from a rover that parked on the moon in 1971. This signal says his heart is beating like he's still on the lunar surface. Run the timestamp, Sully says. Her voice is flat. The specific flatness of someone who already knows the answer is going to be worse than the question. Is this archived data, or is the signal giving us a real-time feed? He runs the timestamp comparison. The vocoder output is not a recording. A recording would have a start point and a fixed duration. It would play and end and either loop or terminate. The vocoder output has been running continuously since the moment he connected the Apollo-era audio processing chain to the signal feed 12 minutes ago, outputting at the current moment, each beat arriving at the moment of its occurrence. Not retrieval, generation. Real time, he says. Sully puts the stylus down very carefully. His heart rate on the lunar surface in 1971 was 72 beats per minute. Average resting rate during EVA-3, yes. The records confirm it. And the signal is outputting 72 beats per minute right now. Yes, that's Dave Scott's pulse. But he's 93 years old. Why does this signal say his heart is beating like he's still on the lunar surface? Thorne does not answer immediately. He is running the vocoder through the second data channel. The signal has more than one audio component. The frequency analysis shows layered structure above and below the cardiac frequency, and the second channel is resolving now through the processing chain, and it is not Dave Scott. It is James Irwin. Lunar Module Pilot, Apollo 15. Irwin died in 1991, a cardiac event at the age of 61. Thorne looks at the waveform from the second channel. The vocoder is outputting James Irwin's cardiac signature at the rate it was running during the third EVA of Apollo 15. Steady, regular, alive. James Irwin has been dead for 35 years. His cardiac signature is running at 68 beats per minute on the right display. Clean, regular. The vocoder is not producing noise or artifact or the kind of degraded output you get when you push a signal beyond its design bandwidth. It is producing 68 clean beats per minute of a heart that stopped in 1991. There's a second channel, Thorne says. Sully leans in. James Irwin, he says. She stares at the waveform, at the 68 beats per minute, at the timestamp on the vocoder output, which is the current time, 0947, a Tuesday morning in November in Worcester, Massachusetts, and the signal is generating this output now, at this moment, in real time. She picks up the stimulant can from the floor and sets it on the bench and does not open it. The clean 72 on the left is the mission commander, she says. The 68 on the right is a dead man. Running at his 1971 surface EVA rate. Running at his 1971 surface EVA rate. She looks at both waveforms, the clean 72 beats per minute of David Scott on the left display, and the clean heart rate of a man who has been dead for 35 years on the right, both of them coming out of a vocoder that is decoding a signal from a rover that has been drawing zero measurable current in storage for 54 years. The moon didn't just record them, she says. Her voice is doing the thing it does when she is narrating something she cannot stop herself from narrating even though the narration is terrible. It sampled them. The rover is the laboratory. The heartbeats play. Left channel, Scott 72, steady. Right channel, Irwin 68, steady. Both rates from 1971. Both rates running now. How many channels does the signal have? Sully asks. Thorne checks the frequency analysis. The signal has structure across a range he has not fully explored. The 1.2 Hz fundamental and its harmonic series are the dominant features, but below the fundamental and above the harmonic ceiling there are additional encoded layers, components that the spectrum analyzer has been displaying as part of the signal's complex architecture without his having decoded them. He runs the full-band vocoder decode across every channel he can isolate. 14 channels. Apollo 15 had a crew of 3. Command Module pilot Alfred Worden remained in lunar orbit. He never touched the surface. Scott and Irwin were the surface crew. 14 channels is not 3. 14, he says. Sully is very still. How many total Apollo surface EVAs were there? He already knows the number. 14. Apollo 11 through 17, excluding 13. 14 surface excursions by American astronauts, each one logged, each one telemetered back to Houston, each one archived in the federal database he has been looking at for the last 12 minutes. 14, he says. Sully pulls up the mission log. She cross-references the channel count against the surface EVA records. Apollo 11, 2 surface crew, Armstrong and Aldrin. Apollo 12, Bean and Conrad. Apollo 14, Shepard and Mitchell. Apollo 15, Scott and Irwin. Apollo 16, Young and Duke. Apollo 17, Cernan and Schmidt. 6 missions, 12 surface crew members, 24 total surface EVAs. But many astronauts completed multiple EVAs, and the signal appears to be keyed to individual astronauts, not individual EVA events. 14 unique individuals, she says. 12 surface crew plus... Wait. She runs the count again. 14 unique individuals walked on the moon. 12 listed crew members, but Gene Cernan walked twice, once on 16 and once on 17, and John Young was the same. And Alan Bean? She stops. No. 14 unique people. 12 mission crew plus... No, it's exactly 12. 12 men walked on the moon. 12 distinct individuals. She looks at the channel count. 14 channels. 2 didn't walk, Thorne says. He is already looking at it. Richard Gordon stayed in lunar orbit on Apollo 12. Ken Mattingly stayed in orbit on Apollo 16. Both crews had command module pilots who never touched the surface. She is quiet. The signal has channels for people who never walked on the moon, she says. Orbital crew. People whose boots never touched the regolith. The rover was on the surface. How did it sample the orbital crew? Thorne looks at the 14 channels. At the 12 surface crew and the 2 orbital crew running their EVA period heart rates in parallel, the signal maintaining the physiological state of every Apollo crew member who was in the lunar system during the landing missions, surface or not. The signal didn't come from the rover, he says. Not originally. The rover is the relay. Whatever sampled the crews sampled all of them, everyone within range of the moon during the missions. The rover is broadcasting the record. The moon made it. The moon has been tracking them. All of them. Since the first boot print. The air filtration exhales. The 1.2 Hertz pulse ticks in the floor. 14 heartbeats play through the vocoder, clean and steady and patient, and one of them belongs to a man who has been dead for 35 years, and the signal does not know that, or does not care, or is maintaining something that death did not close. The rover is still logging the crew, Thorne says. It's not logging current vitals. It's maintaining the mission state data, the last confirmed telemetry from each crew member during their time in the lunar system. Frozen at the moment of departure, running forward from there. He looks at the waveform, at Scott 72, unchanged from 1971. It doesn't know they left. As far as this signal is concerned, they're all still there. All 14 of them, still in the lunar system. Or it knows exactly where they are. Sully says quietly. And it's maintaining a record that doesn't depend on where they went after. She looks at the Irwin channel. 68 beats per minute, clean and steady. James Irwin died in 1991. His heart stopped. The signal doesn't reflect that. The signal is running the last confirmed state. She pauses, which means either the signal doesn't update, it took the sample, and it plays the sample forward regardless of what happened to the original, or she stops herself. Or it knows something about Irwin's state that the cardiac event in 1991 didn't change, Thorne says. She looks at him. She does not answer that. The room is cold and the 14 channels play, and the air filtration exhales its 90-second cycle, and neither of them follows the inference to the end. Not yet. Thorne runs a third decode pass on the sub-fundamental frequency range, below the cardiac data, below the 1.2 Hertz carrier. The vocoder is not rated for this range. He is routing through a modified pipeline. The digital signal processing stack extended beyond its design parameters to push the audio chain into frequencies it was not built to handle. The output is degraded, partial, not a clean decode. It is enough. Respiration. 14 respiration traces, 1 per cardiac channel. Each one the breathing rate of a specific astronaut during their surface EVA. Each one frozen at the mission state value and running forward from there. The same logic as the cardiac data, the same frozen moment, the same patient replay of a biological state that ended for most of these men decades ago. He sits with the full picture for a moment. The signal is not carrying a radio transmission. It is not carrying a navigation update or a telemetry log or a data archive in any format he has worked with. It is carrying human beings, or the most precise available facsimile of human beings at a specific moment in time, encoded in a gravitational carrier wave in the central logic unit of a 1971 lunar rover, maintained in real time by a non-terrestrial crystal growing roots into 50-year-old silicon at 2.1 terahertz, and transmitted continuously to the Hadley-Apennine landing site on the moon. The moon has not just recorded them, it is keeping them. The moon didn't just record them, Sully says. She is still looking at the 14 channels, at Scott and Irwin and the 12 others, running their EVA heart rates into a Tuesday morning in November with no indication of ever stopping. It sampled them. The rover is the laboratory. He looks at the CLU housing, Recapped. Sealed. The shard behind it still growing its roots, still recruiting the last Fairchild gates, still running the 14 channels and the gravitational map and the bidirectional dish traffic, all of it simultaneously. All of it from one black crystal the size of a fist that was placed in a NASA computer before the rover left the ground. 44 hours until the integration is complete. He does not know what happens to the 14 records when there are no more gates left to recruit. He does not know if the records stay in the signal or go somewhere else. He does not know if the moon has been waiting to receive them or has been receiving them all along. The 14 heartbeats play through the vocoder, Scott at 72, Irwin at 68, 12 others at their own rates, all of them steady, all of them patient. The vocoder outputting clean audio at 9:47 on a Tuesday morning in a cold room in New England. Thorne checks the integration clock against yesterday's gate migration rate. The calculation puts full die integration at approximately 1900 hours tonight, not 44 hours from the Chapter 9 estimate. The gate migration accelerated after the endoscope insertion. The housing port disturbance he predicted. The shard is running faster now. 10 hours, not 44. Sully. He turns the integration timeline estimate toward her. The migration rate updated overnight. She reads the number. She reads it twice. Her hand goes to her stimulant can, finds it empty, puts it down. 10 hours, she says. Approximately. The endoscope insertion changed the boundary condition. The migration rate increased by factor of 4.3 after we recapped the port. She looks at the 14 channels, at the heartbeats of 12 men who walked on the moon and 2 who orbited it, and 1 who has been dead for 35 years. All of them running at their 1971 surface rates, all of them maintained by a crystal in a housing in this room that has 10 hours left before it finishes recruiting the last of the silicon it needs. What does it do in 10 hours? She says. I don't know. Then we have 10 hours to find out. The 14 heartbeats play. Chapter 11. The Lunar Ping. The satellite uplink confirms a simultaneous 1.2 Hz pulse from the Hadley-Apennine landing site, and Sully does not say anything for a long moment, which is unlike her. Thorne reads the return data over her shoulder. The interferometric satellite, a commercial gravitational background survey platform, the closest instrument to what they needed, has been in play since day 9, when Sully submitted the detection request the morning after the dish went active. It took 2 days to configure the targeting parameters, 2 days to get the request into the satellite's scheduling queue, and another day waiting for the orbital geometry that would put the instrument in a position to detect a gravitational signal at the Hadley-Apennine coordinates. The detection window opened 43 minutes ago and closed 32 minutes later, and the data came down during the pass. The return data is unambiguous, a gravitational pulse at 1.2 Hz, originating from coordinates centered on the original Apollo 15 parking spot, transmitting simultaneously with the rover in this room, not an echo of the rover's outbound signal. The satellite's temporal analysis distinguishes reflected signals from independent sources at the precision needed for gravitational wave background work, and it has flagged this as an independent source with high confidence. Something at Hadley-Apennine is running the 1.2 Hz signature on its own, right now, as this room produces the same frequency from the chassis on the platform. The packet structure is different from ours, Sully says. She has found her register, flat, precise, reading the data aloud so the shift log captures it. The outbound signal from our dish and the incoming signal from Hadley-Apennine are not the same transmission. They're distinct packets, exchanging data in both directions, structured as a conversation, not as a broadcast. She pulls up the header analysis. The protocol is the same, 2026 AES architecture, but the keys are different. The Hadley-Apennine source has its own encryption key. It's an independent transmitter in an active bidirectional exchange with our dish. Triangulate the source, Thorne says. She runs the triangulation using the satellite return geometry, cross-referenced against the rover's known outbound angle. The result renders on the primary display. It is not the rover. The source at Hadley-Apennine is not a point. The satellite's resolution is sufficient to indicate a spatial distribution, a footprint. Thorn looks at the footprint and compares it against what the Apollo 15 mission left at the landing site. The rover is a few meters across. The ALSEP instrument package is a few meters across. The descent stage is a few meters across. Everything human at that site is human-scaled. The footprint on the display is not human-scaled. It's massive, Sully says. Her voice has the specific quality it gets when she's reading a number off an instrument and needs a moment to accept the instrument is correct before she says it out loud. The source footprint is, it's not rover scale, it's not instrument scale, it's not anything the Apollo 15 mission deployed or left behind. Whatever is at the Hadley-Apennine site is large. Very large. The satellite's resolution doesn't give us a precise dimension. It was optimized for cosmological sources. But the footprint it's resolving is orders of magnitude larger than any human artifact at that location. She looks at the triangulation result. There is a massive structure at the Hadley-Apennine landing site that is in active bidirectional communication with this rover. It is not ours. It was not there in 1971 because we would have noticed it in 71. It is there now. Thorn looks at the display. He looks at the footprint. The rover is transmitting to it, he says. The rover has been transmitting to it since the dish went active, since the bypass opened, possibly since before we opened anything. The 1.2 Hz baseline signal, the pre-bypass transmission through the relay gap, all of it may have been addressed to this structure. We have been watching the rover talk, and the structure has been answering, and we did not know the structure existed until this morning. She pulls up the signal history from the dish, the directional data, the transmission logs, the pattern of outbound packets the shard has been generating and sending upward for 11 days. Every packet the rover has sent since the dish went active has been addressed to this location. Every response we couldn't decrypt came from this location. She looks at the CLU housing, at the recapped endoscope port, at the sealed aluminum box running its 2.1 terahertz processing cycle. The shard has known about this structure since the moment it powered up. The shard was planted in the CLU housing before the rover left the ground. The shard's root network was established at initialization. The addressing information, the destination for every outbound packet, was built into the shard's architecture before Apollo 15 launched. The shard knew where to find the structure before the rover existed as an assembled object. She pauses. We did not build a connection to this structure. The connection was already built. We just opened the hardware it was waiting to run through. The 1.2 Hz pulse ticks in the floor. Thorn looks at the triangulation result, at the confirmed simultaneous source at Hadley-Apennine, independent, active, massive, exchanging structured data with the rover through a 2026 encrypted protocol. He looks at the whiteboard, at the column of entries from 11 days of investigation. He picks up the marker. Simultaneous source confirmed. Hadley-Apennine. Independent transmitter. Structure, massive. Bidirectional exchange, active. Rover, 1 node. He draws a line under it. The rover isn't a transmitter, he says. It's been a terminal the entire time. 1 node in a network that has been live since the moment the rover reached the lunar surface in 1971. He looks at the display. At the Hadley-Apennine source. At the 2 endpoints of an active connection, one in this room, one on the moon, both running the same frequency, both part of the same system. The network isn't the rover. The rover is how we found the network. He looks at Sully. The question is whether there are other nodes. I've been thinking about that. She pulls up the mission inventory, the list of Apollo hardware that touched the lunar surface or entered the lunar system. Every landing mission deployed hardware at the site. Every landing mission had a CLU. If each CLU carries a shard, if the pattern we've found in LRV-02 repeats across the program, each shard would have a corresponding structure at its site, Thorn says. Thorn exhales. The room is cold, 33 Fahrenheit. The climate system running at maximum and losing ground. The shard in the housing pulling thermal energy from everything within radius. He watches his breath fog and thinks about the number Sully just said. 6 missions, 6 CLU packages, 6 shards, if the pattern holds. 6 structures, if the pattern holds. 6 active connections between hardware they built and something on the moon that is not theirs. Each shard, each structure, each site. She is running it as she says it, pulling the Apollo mission hardware inventory, the CLU package specifications, the list of missions that carried the Fairchild processor package in the lunar systems. Apollo 11 through 17, minus 13 which never landed. 6 missions, 6 CLU packages on the surface or in transit home. If every CLU carries a shard, if the pattern isn't unique to LRV 002, then there are 5 more active nodes. She stops typing. 5 more shards, 5 more structures, 5 more active connections between hardware we built and structures we've never seen. She looks at him. The rover isn't a node in a local network. It's a node in a network that covers every Apollo landing site on the lunar surface. A pause, then flat and certain. The network is live across the solar system. The words sit in the room with the cold and the pulse and the 14 cardiac traces playing through the vocoder on the bench. 14 heartbeats from 14 astronauts, all of them frozen at their mission state rates, all of them maintained by the shard in the housing, all of them part of a network that Sully has just named with a scope that neither of them has fully absorbed yet. A network covering every Apollo landing site. A network that has been live since the first mission touched the moon. A network that the shard has been running this entire time, one node, sending and receiving, while they stood 6 feet away and tried to understand the phone without knowing the caller existed. Thorne exhales. His breath fogs. He looks at the Hadley-Apennine source on the display, at the massive structure in active correspondence with the shard behind the sealed CLU housing in this room, processing incoming data at 2.1 terahertz through a root network grown into 50-year-old silicon, building toward an integration endpoint he still cannot predict. The network has been live since the first mission landed. They have been inside it for 11 days without knowing it was there. We need the incoming signal decoded, he says. Whatever the structure is telling the shard, whatever instructions or data are coming down through the dish, I need to know what the shard knows. He looks at the housing, at the sealed port, the cold aluminum surface, the bit depth counter at 108. We have been operating this terminal for 11 days. We have been interpreting our actions as investigation. We have been making decisions, opening the bypass, running the endoscope, staying inside the Faraday cage, and calling those decisions ours. He looks at Sully. If the shard has been receiving instructions from the structure for 5 days, and the structure's instructions are encrypted and we cannot read them, then we cannot verify that our decisions have been our decisions. We cannot confirm that the actions we've taken since the bypass opened were not actions the network wanted us to take. He puts the marker down. We are managing a terminal in a 54-year-old network we don't understand, for a purpose we haven't identified, and we cannot read the operational instructions. A pause. That is not an acceptable state. Sully is quiet for a moment. She is looking at the dash transmission log, at the record of every packet the rover has sent and every packet it has received since the dish went active. Hundreds of exchanges. Structured, encrypted, continuous. The shard sending data up, the structure sending data down. The shadow logic network processing the return feed at 2.1 terahertz inside a sealed housing in this room. The bypass, she says. Day 6. You decided to open the relay bypass. I decided to open the relay bypass. The Faraday cage. Day 4. You put the rover in the cage. The cage amplified the signal. He looks at her. Yes. And we established that the cage amplifying the signal was the expected physical consequence of putting a gravitational transmitter inside a resonant copper enclosure. We knew going in that it would probably amplify. You decided to do it anyway because the data required empirical verification. Yes. The shard has been receiving encrypted instructions from the structure for 5 days. The structure has been in active communication with the shard since before we were born. She looks at the transmission log. I cannot tell you with certainty that the instruction to open the bypass came from you and not from the network. I cannot tell you that any decision we've made since day one was not a response to something the Shard was instructed to make us do. She closes the log. I am not saying it did. I am saying I cannot rule it out. And I cannot rule it out because I cannot read the incoming messages. Thorn looks at the housing, at the sealed port, at the Shard behind it. Then we decode the messages, he says. Sully looks at the decode failure log. 5 days of attempts, 37 distinct decode strategies, every variation of the 2026 architecture she can construct from the published draft and the signal header data. Everyone returned noise. The Shard holds the key, and the key is internal to the shadow logic architecture and exits through no interface she can reach. She has known this for 5 days. She has kept running attempts because stopping felt worse than failing. The Shard is the only thing in this room that can decrypt the incoming data, she says, and the Shard is not going to give us the key. She closes the failure log with the specific deliberateness of someone setting down a tool that has done everything it can and picking up a different one. The direct approach is exhausted. We read the actions instead. Every gate migration, every thermal draw fluctuation, every change in the Shard's processing load is a response to incoming data. If the responses have a pattern, the pattern encodes the content. 11 days of behavioral data is a long letter written in a language we might be able to learn. She looks at him. We decode the translation. Thorn looks at the housing, at the bit depth counter at 108, at the integration clock. Start the behavioral analysis, he says. We have the SEM data, the gate migration patterns, the thermal draw history, the dish transmission logs. We have everything the Shard has done for 11 days. We do not have what it has been told. We work from what we have. The behavioral approach. She is already pulling the data sets, running a compilation query across every instrument log from day one. If we can't read the incoming messages, we read the responses. Every gate migration event, every bit depth increment, every change in thermal draw, all of it is the Shard responding to something. If the response patterns are consistent, if there's a logical structure to what the Shard does after receiving data, we can reverse engineer the content from the behavior. She looks at the volume of data she's compiled. 11 days. Every measurement we've taken. It's the Shard's behavioral record since we first touched this hardware. A pause. It's also the network's behavioral record. The Shard is one node. What the Shard does is what the network instructs it to do. She looks at him. We might not be reading a terminal's behavior. We might be reading the network's. Thorn picks up his marker one more time. He writes under the last entry. Approach. Behavioral analysis. Target. Shard response patterns. Hypothesis. Reverse engineer network instructions from output. He draws a line under it. The network is live. The structure at Hadley-Apennine is transmitting. The Shard is processing incoming data at 2.1 terahertz through roots grown into 50-year-old silicon, and the integration clock is running, and Thorn has 11 days of behavioral data on a terminal in a network that has been operational since the first Apollo mission reached the moon. He does not know what the network is for. He has to find out from the wrong end before the Shard finishes. The bit depth counter ticks. 108. Chapter 12. The Genetic Handshake. The biolab returns a match on the DNA sequencing, and the match is David Scott. Not a partial match, not a statistical correlation. The quantum microscope analysis of the biometallic residue, the silver ferrofluidic material that was coating the bus bar terminals when Thorn stripped the Mylar 12 days ago, the material that pulsed at 1.2 Hz under UV light, the material that bled when the laser bridged the relay bypass, contains a complete, intact, high-fidelity DNA sequence, and the sequence, cross-referenced against the genomic database Thorn pulled from the NASA Medical Archive, matches the mission commander of Apollo 15 at a confidence level the sequencing software reports as 1.000 before he can stop it from rounding. The software does not round to 1.000 for anything. It rounds to 1.000 for nothing. Thorne has used this software for 9 years, and the highest match he has ever seen it return was 0.997 on a reference standard. He calls Sully in from the signal lab. She reads it. She reads it again. She picks up her stimulant can, finds it empty, and sets it back down. "Run it on the whole sample," she says. "Full residue bank, all the specimens from the bus bar isolation." He has already run it. He queued the full specimen bank the moment the first result came back, because the first result told him everything about what the full result would say, and he needed the confirmation before he said it out loud to anyone, including himself. The results render one by one. David Scott, James Irwin. David Scott again, second specimen, same confidence level. James Irwin, third specimen. He keeps watching. A fourth sequence appears, different profile. He runs the cross-reference against the Apollo 15 medical records. Alfred Worden, command module pilot, the man who flew the Endeavour command module while Scott and Irwin drove the rover across the Hadley-Apennine plain, the man who orbited the moon at 110 kilometers altitude, who never set foot on the surface, who never sat in the rover's seat or touched the rover's handlebars. Worden's DNA is in the biometallic coating of the rover's primary power bus, the coating that was sealed under the Mylar insulation before the rover shipped to the launch site. Worden never touched this rover, Sully says. She has found the access log herself, pulling it while the sequencer was still running. No. His DNA is in the coating anyway. Yes. She sets the access log down. She stares at the specimen results. At 3 Apollo 15 crew members encoded in a silver biometallic substrate bonded to the copper bus bars of the rover's primary power circuit. She looks at the specimen results. At 3 Apollo 15 crew members encoded in a biometallic substrate bonded to the copper bus bars of the rover's primary power circuit. At 3 human beings, one dead for 35 years, one in his 90s, one still living, present at the molecular level in a material that pulsed and bled and avoided UV light and moved like tissue. "When was this deposited?" she says. "The material was under the Mylar. The Mylar was in place before the rover shipped. We established in Chapter 2 that the Mylar adhesive was still active, undegraded, because it had been sealed. The coating was sealed inside the Mylar insulation for 55 years. She looks at the specimen log. The crew members whose DNA is in this coating, did they have physical contact with the rover before launch? Thorne pulls the NASA pre-launch records, the crew access logs, the assembly and checkout documentation, the inspection records from the Boeing facility. Scott and Irwin conducted pre-launch checkout on the rover. They sat in the seats, tested the controls, verified the instrument panel. Standard procedure. They touched the handlebars, the seat frames, the instrument housings, skin contact with the aluminum chassis. Worden's record is different. Worden's pre-launch access log shows one visit to the rover assembly station, a brief walkthrough, no recorded contact with the hardware. The log notes him as a bystander during a checkout review. He stood near the rover. He did not sit in it. He did not touch it. His DNA is in the coating anyway. It sampled the air, Thorne says. The biometallic material was active during pre-launch assembly. It was collecting biological data from the surrounding environment, shed skin cells, exhaled cellular material, ambient biological traces. It sampled everyone in proximity. He looks at the residue specimens. Not just the crew. Everyone in the Boeing assembly facility during that period is potentially in this coating. But we matched 3 Apollo 15 crew members, because those are the sequences we have reference data for. He looks at the specimen bank. There may be dozens of sequences in here, hundreds. Every technician, every engineer, every inspector who was near this rover during assembly. The rover remembered everyone who was near it, Sully says quietly. The rover sampled everyone who was near it, and stored the samples in a biometallic substrate that was sealed under Mylar and has been preserved at near-perfect fidelity for 55 years. He picks up the quantum microscope feed. At the maximum magnification, the biometallic residue is not a uniform material. It is structured, cellular in organization, each discrete element containing what the microscope's analysis software is flagging as a complex molecular payload, not just DNA. Proteins, long-chain molecules with a base architecture that matches terrestrial biochemistry at the broad structural level and diverges from it at the fine level, the way a translation diverges from an original, the same grammar, different vocabulary. Non-terrestrial proteins. Modified sequences. Human DNA carrying molecular additions that did not come from any human genome and did not come from any organism in the genomic reference library. He cross-references against every database the facility has access to: bacterial, archaeal, viral, synthetic, the full breadth of documented biology on Earth, and the flagged regions match nothing. The additions are not mutations. The additions are not errors. The additions have the structural characteristics of deliberate insertions. Sequences integrated at specific positions in the stored human DNA with a precision that implies intention. The DNA is modified, Thorne says. Sully is already at the protein analysis panel, moving fast, the stream of consciousness register fully open. I see it. The non-terrestrial insertions they're at multiple loci, they're not random. The insertion positions are Elias. The insertions are at the same relative positions across all three crew member sequences: Scott, Irwin, Worden. The non-terrestrial additions are at corresponding positions in all three genomes. The same modification pattern applied to three different human genetic profiles. She highlights the regions. This isn't contamination. Contamination is random. This is systematic. Something applied a specific modification protocol to every sample it collected. She is looking at the protein analysis, at the sequence flags, at the non-terrestrial tags embedded in the stored genetic data. The human sequences are intact, full fidelity, no degradation, exactly what you'd find in a fresh sample from a living person. But there are additions, molecular additions to the stored sequences that are not part of the original human genome. She highlights the flagged regions. They're not mutations. They're not transcription errors. They're deliberate insertions, sequences that were added to the stored human DNA at some point after collection, added and preserved in the same substrate. She looks at the screen. Something took the biological samples and modified them. Something annotated the human DNA with non-terrestrial information and sealed it in the coding and waited. The 1.2 Hertz pulse ticks in the floor. Thorne looks at the specimen results. At 3 crew members and whatever additional population the coding contains, the Boeing engineers, the NASA inspectors, every human being who came within biological sampling range of this rover during assembly, all of them in the biometallic coding, all of them present, preserved, modified. What do the non-terrestrial sequences encode? He says. I don't know yet. The protein structure is unlike anything in the reference library. I can characterize the molecular architecture, but I can't interpret the function without a reference frame for this biochemistry. She is pulling comparison data, running structural analysis, looking for any analog in the known biological databases. But the organization is consistent with data storage. The molecular structure of the non-terrestrial insertions has the information density characteristics of a biological data format. It's not functional protein. It's recorded information. The human DNA has been annotated, tagged, written in. Thorne sets down the microscope feed. He looks at the rover, at the chassis, the bus bars, the terminal housing, all of it built by human hands, assembled in Worcester, certified and launched and driven across the lunar surface by 2 men who did not know the machine was taking notes. The biometallic coating collected their DNA, modified it, stored it, sent it. The 14 cardiac channels from the vocoder, the biological telemetry in the dish transmission packets, all of it ultimately sourced from this material, all of it drawn from the stored genetic records of everyone who came near this rover before it left the ground. The biometallic residue is not infrastructure. It is not a seal or a protective coating or a byproduct of the signal architecture. It is a sample collection system. The moon didn't just record them, Sully says. Her voice is flat, reading a conclusion she has reached and does not want to say, but has to. It sampled them. The rover is the laboratory. The network is live. The structure at Hadley-Apennine is receiving transmissions. The shard processes incoming instructions that they cannot decrypt. The biometallic coating has been collecting and preserving and annotating human biological material since before Apollo 15 launched. Thorne looks at the specimen results. At David Scott and James Irwin and Alfred Worden, present at the molecular level in a coating on a bus bar in a clean room in Worcester. Present, not archived, not recorded. Present, maintained in the substrate, preserved against degradation for 55 years at fidelity that the sequencing software cannot distinguish from a fresh sample. The data packet, he says. The 14 cardiac channels the vocoder decoded, the biological telemetry and the dish transmission packets. If the signal is built on stored genetic data from this coding, if the heartbeats are derived from the DNA-level records of the crew rather than from actual biometric telemetry, then they're not recordings, Sully says. She has been arriving at this for the last 30 seconds, and her voice is the voice of someone who has arrived at something and wishes the journey had been shorter. The signal isn't replaying what the biomed harnesses transmitted to Houston in 1971. The signal is a reconstruction. The shard is running generative models of the crew from their stored genetic data, generating the cardiac and respiratory traces from biological first principles, and transmitting those models to the structure at Hadley-Apennine. She stares at the specimen log. It has enough genetic information to model them. The DNA, the non-terrestrial modifications, whatever those encode, it's enough to run them forward, to keep them running, to keep them generating output that looks exactly like a living heart rate, because it is derived from the same biological source as a living heart rate. She looks at the vocoder bench, at the 14 channels playing, at the Irwin channel at 68 beats per minute. James Irwin died in 1991, she says. His heart stopped. The signal doesn't know that. The signal isn't based on his actual heart. It's based on his stored genetic data and the model derived from it. The model doesn't include his death because his death happened after the sample was taken. The model just keeps running from the last known state. A pause. 68 beats per minute, forever, or until the shard runs out of power, or until the network tells it to stop. She looks at Thorne, the non-terrestrial proteins, the molecular additions to the stored DNA. Whatever they encode, that's the information the structure at Hadley-Apennine has been receiving, not just the cardiac trace, the full biological model, the annotated genome, everything the biometallic material collected and modified and preserved for 55 years. The Irwin channel plays, 68 beats per minute, steady and patient, running forward from a sample of a man taken before he knew he was being sampled, in a building he visited once to stand near a rover he never touched, preserved in a silver coating that pulsed under UV light and avoided ultraviolet exposure and moved like tissue when the laser bridged the bypass terminals. The Apollo missions were a harvest, Thorne says. Nobody answers. The room is cold. The vocoder plays its 14 channels. The specimen results are still on the primary display. David Scott, James Irwin, Alfred Worden, their genetic data preserved at fresh sample fidelity in a biometallic coating that has been in this building for 31 days on this bench, 2 meters from where Thorne has been standing for most of those days. He looks at his own hands. He has been in physical proximity to the biometallic material since the Mylar removal on day 2. He has been working in a room where the material is present in isolated specimen jars on the bench, where the same coating was on the bus bars until the laser bypass opened it, where the ferrofluid that bled from the relay terminals flowed into an isolation bag that is still in the equipment locker. 12 days of proximity to an active biological collection system. He has not been sampled. He has no reason to believe he has been sampled. The biometallic material on the bus bars has been isolated since the Mylar removal. The specimen jars are sealed. The ferrofluid is contained. He has no reason to believe he has been sampled. He looks at Sully. She is looking at her own hands. The behavioral analysis, he says. We started it this morning. The response patterns from the shard. We work from that. He puts the specimen results in the log. He puts the non-terrestrial protein analysis in the log. He writes the checkmate on the whiteboard because the log requires it, and the whiteboard requires it, and because writing it makes it real in the way that real things need to be. Harvest. Biometallic residue. Collection system. Stored samples, modified. Non-terrestrial annotations, present, transmission, target, Hadley-Apennine structure. He draws a line under it. He does not look at his hands again. He keeps his eyes on the whiteboard. The pulse ticks in the floor, in the bench, in the specimen jars, 1.2 Hertz. The network has what it came for. It has had it since 1971. Whatever comes next is not the collection. Chapter 13. The Escalation. The I-beam in the northeast corner of the clean room is no longer steel. Thorne finds it during the morning structural survey, a routine he added to the inspection protocol on day 10 when the chassis conversion monitoring required him to be near the walls anyway. He runs the contact hardness probe along the base of each exposed structural column as part of the circuit. He has done it every morning for 4 days. Every morning the columns have returned the same reading. High-carbon structural steel, consistent with the facility's construction specification, nothing anomalous. This morning the northeast column returns no reading, not a 0, not a below threshold. The probe's sensor makes contact with the column surface and the display shows a dash, the symbol the instrument uses when the material under the probe has no analog in its reference library. Thorne presses harder. The display shows the dash. He moves the probe 2 centimeters along the column surface. The dash again. He moves to the undisturbed steel section 30 centimeters up the column, and the instrument returns the expected high-carbon reading immediately. He looks at the section of column between floor level and approximately 30 centimeters up. It is translucent, not the dull gray of painted structural steel, not the flat industrial finish of a building component that has been standing in this room for 12 years. Translucent. The same deep internal translucency as the crystalline bus conductors in the rover chassis. The same faint luminescence that he has been documenting since day 2 when the Mylar came off and the copper wiring was gone, and what was left in its place caught the LED light from the inside. The lower 30 centimeters of the northeast structural column have been converted to crystalline material. The conversion is complete, not a partial transition, not a boundary zone, not a region where the steel grain structure is beginning to change. The steel is gone, the crystal is there. He holds the hardness probe against the converted section for 10 full seconds. The display shows the dash for all 10. He records the reading in the log. He does not touch the surface with his bare hand. He runs the UV wand over the converted section. It pulses. 1.2 Hertz. The same frequency as the signal in the rover chassis 6 meters away. The same frequency as the gravitational pulse in the floor and the walls and his sternum. All of it synchronized. All of it one system. The system now includes this column. Sully. He keys the intercom. I need you in the clean room. She arrives in 4 minutes. She looks at the column. She does not say anything for a moment. The anchor bolts, she says. She is already crouching at the base of the column, running the UV wand along the base plate. The base plate pulses, the full surface, edge to edge, conversion complete. We logged the specimen platform anchor bolts as crystalline 2 days ago. The network had extended through the bolt material into the floor substrate. We noted it. We were tracking the rover chassis conversion, and we tracked the anchor bolts as part of that. She traces the UV wand upward from the base plate along the column face, following the luminescence. The column sits on a base plate that is anchored to the same floor slab as the specimen platform. The anchor system is continuous, specimen platform to floor substrate to column base plate to structural column. She stands. The network used the physical anchor connection as a transmission path. It grew through the floor, through the base plate, and into the structural steel of this column. She looks at the conversion boundary 30 centimeters up. We were watching the rover. The network was routing through the floor. She exhales. The rover's crystalline network is not confined to the rover. It has extended itself into the facility's structural system. Thorne looks at the column, at the 30-centimeter translucent section, at the boundary line between converted and unconverted steel, a clean horizontal interface approximately 30 centimeters above the floor, the crystalline material below it, and the original structural steel above it. The two materials meeting at a boundary that is not a joint or a weld or any human-made connection. The boundary the conversion front has reached so far How far has it spread? He says. She runs the UV wand in a slow circuit around the room, pausing at each structural column base. The clean room has 6 columns, 1 in each corner and 2 midspan on the longer walls. She checks each base plate, each lower column section, each anchor point. 4 of the 6 columns are converted in the lower section. Northeast corner, the first one he found, 30 centimeters of converted steel, full translucency, UV pulse confirmed. This is the column closest to the specimen platform. Northwest corner, conversion present, approximately 25 centimeters, same profile. East wall midspan column, conversion present, approximately 15 centimeters. Luminescence slightly dimmer than the corner columns, conversion less advanced. North wall midspan column, conversion present, approximately 8 centimeters. The crystalline material still showing some heterogeneity at the upper boundary. The conversion front actively progressing. Southeast corner, original steel. Hardness probe returns the expected high carbon reading at every point. Southwest corner, original steel. The 2 farthest columns from the specimen platform are still steel. The 4 nearest are crystalline to varying heights. The conversion front is radiating outward from the rover's position, progressing through the anchor and base plate system, climbing the structural columns at a progression that tracks proximity to the source. Sully finishes the survey and stands in the center of the room and looks at the 4 converted columns. The clean room is inside the network, she says. It is not a new conclusion. It follows directly from what the column measurements show, but she says it out loud anyway because it is the kind of thing that needs to be said out loud. The building that was built to contain this investigation is being incorporated into the system it was meant to isolate. Sully is at the specimen platform. She runs the hardness probe along the platform frame, the mounting brackets, the floor contact points. The probe returns the dash at every point on the platform surface. Not some points, every point. The full perimeter of the stainless steel specimen table, every contact surface between the table and the floor, and between the table and the rover's chassis. The platform is crystalline from the floor, contact points upward. She measures with the wand along the table leg height. Converted to approximately halfway up the legs, the crystalline material meeting unconverted stainless steel at a clean boundary at mid-leg. The platform is converting, she says. Her voice is the flat, fast register, the one she uses when the data is running ahead of what she can do about it. The rover isn't sitting on a steel table anymore. It's sitting on a table that is part of the same network as the column bases. The crystalline material runs from the rover chassis, contact points down through the platform legs, through the floor substrate, through the base plates, up into the structural columns. She pauses. There's an unbroken crystalline pathway from the CLU housing in the rover to the structural skeleton of this building, right now, while we're standing in it. She looks at him. The Faraday cage was supposed to contain the signal. The building was supposed to isolate the rover. The specimen platform was supposed to be a neutral substrate. She looks at the table legs, at the boundary between crystalline and stainless at mid-leg height. We put the rover on a steel table in a building with steel columns and anchored everything to a common concrete substrate, and the network used every single connection we gave it. Thorne looks at the northeast column, at the luminescent 30-centimeter section, at the clean horizontal boundary line where converted crystal meets unconverted steel, approximately 30 centimeters above the base plate, 4.5 meters below the structural beam that runs between the columns at ceiling height. The conversion front has been advancing upward for some period of time. He cannot determine without more data. He does not know when this column first began to convert, does not know if it started last night or 3 days ago or the moment the rover arrived, does not know the rate. What he knows is the direction. Upward. The thermite is wired to the CLU. The CLU is in the rover. The rover is on the platform. The platform is crystalline from the floor contact upward. When the platform conversion completes the table legs, the rover and the platform and the floor substrate and the column bases will all be part of one continuous crystalline network. At that point, burning the CLU burns one node in a network that runs through the structural steel of an occupied building. He does not know what that means. He has not had to know it yet. He does not know what a thermite charge does to a crystalline network that runs through the structural columns of an occupied building. He knows what thermite does to a CLU housing. It burns, it melts. The aluminum housing and the silicon substrate and the crystalline roots are destroyed at temperatures that leave nothing recoverable. He knows what thermite does to the CLU. He does not know what happens to the parts of the network that are not in the CLU. The crystalline conductors in the rover bus bars, the biometallic coating on the terminals, the anchor bolts in the floor substrate, the 30 centimeters of crystalline material in the northeast column. He does not know if destroying the CLU collapses the network or severs it, or leaves it running through the structural steel without a shard to coordinate it. And he does not know if a severed network in structural steel is worse or better than an active one. He does not know, and he has been cataloging things he does not know for 14 days, and the list has not gotten shorter. The list has gotten longer. The list has grown the way the network has grown, one item at a time. Each new thing he does not know connected to the things he does not know before it, all of it pointing toward a completion event he cannot see from this side of it. Document it, he says. Full survey, every column, every contact point, every conversion boundary, heights, UV response, hardness probe readings. I want a complete map of the network extent in this facility right now, before the next conversion event advances the front further. She starts the survey. She has her probe kit and her UV wand and her camera, and she begins at the northeast column, works clockwise, pausing at each column base, each anchor point, each base plate. She does not rush. She has been documenting things she did not expect for 14 days, and she has learned, they have both learned, that the methodology requires not rushing even when the thing being documented is unexpected, at a scale that makes the previous unexpected things feel manageable by comparison. Thorne documents his own observations in the shift log while she works. He writes the column conversion heights. He writes the platform conversion height on the table legs. He writes the anchor bolt conversion status, updating the prior entry from 3 days ago when he logged it as crystalline material growing through bolt substrate into concrete, without full appreciation of where that growth was heading. He was not wrong then. He was just not far enough along the chain to see the column at the end of it. He was documenting each link as he found it, and the chain was leading somewhere he could not see from the link he was standing on. He can see it now. He writes, facility structural columns partially converted. Northeast, northwest, east midspan, north midspan. Conversion via anchor system. Specimen platform, legs, converting. Unbroken crystalline pathway from clue to structural skeleton, confirmed. He reads it back. He does not draw a line under it. There is nothing resolved here to draw a line under. She finishes the survey. She reads back her measurements. He compares them against his. The data is consistent. The map is complete. The network extends through 4 of 6 structural columns to varying heights. The specimen platform is converting at mid-leg. The 2 remaining original steel columns, southeast and southwest, are the farthest from the rover and have not yet been reached. The 2 clean columns, she says. How long before the network reaches them? I don't know. What do we do when it does? He looks at the CLU housing, at the thermite circuit indicator, green, armed, the trigger in her hand, at the northeast column glowing its 1.2 Hertz pulse in the LED light, at the 2 clean columns across the room, still dark, still steel, still exactly what the building's construction drawings say they should be. I don't know, he says again. The honest answer has been the same answer for 14 days. Thorne watches her work and looks at the rover, at the chassis on the platform, old aluminum, aged wire mesh wheels, the Mylar insulation that was pristine and supple under its 55-year seal, the communications dish angled toward the ceiling, the machine that came from the moon, the machine that has been in this facility for 31 days and has spent those 31 days routing its crystalline network through every physical connection available, the bus bars, the relay housing, the bypass circuit, the antenna stack, the specimen platform, the anchor bolts, the floor substrate, the base plates, the structural columns. 31 days to reach the building's skeleton. He thinks about the other rovers, about LRV-01 at the Smithsonian and LRV-03 at the Kennedy Space Center, about the Apollo descent stages still on the lunar surface at the landing sites, all of them carrying shards, potentially, all of them sitting in buildings or on regolith that has physical connections to something. He does not say this out loud. The survey will take an hour, and he does not want to interrupt the survey with something that cannot be addressed in the next hour. He writes it in the shift log instead. 3 lines. He reads them back, and they are correct, and he closes the log. The bit depth counter reads 117. The northeast column pulses at 1.2 Hertz, steady and patient. The building is part of the network now. The southeast and southwest columns are still steel. Sully is looking at them from across the room. Thorne is looking at them too. They are still steel. For now. Chapter 14. The Escalation. The clock on the primary monitor is running backward and has been for 47 seconds before Thorne notices. He notices because Sully says, "That's wrong," in the specific voice. Not alarmed, not uncertain. The voice she uses when something on a display has violated a physical rule, and she has already verified it twice before speaking. He looks up from the shift log. He looks at the clock in the upper right corner of the primary monitor and watches the seconds decrement. Not the time running forward with a transient glitch, not a display artifact from the signal interference they have been living with for 2 weeks. The time is running backward. Each second subtracts from the previous, the display rolling from the current value downward, the minutes following, the hours following, the timestamp retreating through the morning at a steady 1 second per second rate in the wrong direction. He checks his wrist monitor. Current time, advancing normally. He checks the instrument bench clock, analog, mechanical, battery-powered, isolated from every network connection in the facility. The instrument bench clock shows the current time, advancing normally. He checks the secondary monitor, running backward, tertiary monitor, backward, environmental control panel on the south wall, backward, HVAC status display, backward, the specimen room environmental logger, backward. Every digital clock in the clean room that is networked to the facility's infrastructure is running backward. Every clock that runs on the facility's electrical distribution receives its NTP sync through the facility network, draws power from the facility grid, is retreating through time at 1 second per second. The mechanical clock on the bench, drawing power from its own battery, synchronized to nothing, is correct. The dividing line between correct clocks and incorrect clocks is the facility power grid. It started 47 seconds ago, Sully says. She's been timing it. She is at her station with her tablet, the tablet showing the current correct time because she disconnected it from the facility network on day 9 as part of the air gap protocol, and it has been running on its own internal clock since then. The tablet is correct, the networked clocks are not. The facility network clocks all flipped simultaneously. I checked the server room status remotely. The NTP server is showing a healthy sync. Its internal timestamp is running forward. The correct time is being broadcast to the facility network every 60 seconds. The networked clocks are receiving a correct timestamp and displaying a backward one. She looks at the monitor. The clocks are not malfunctioning. The display layer is being overridden. Something is telling every network display in this building to show the time running backward. Thorne looks at the primary monitor, at the timestamp retreating through the current minute, rolling back through the hour, the values diminishing. He watches it for 10 seconds. He looks at the northeast column, still glowing its 1.2 Hertz pulse in the LED light. He looks at the rover, at the CLU housing, at the shard behind the sealed port. What time is it running toward? He says. Sully is already on it. She extrapolates the rate of descent, the seconds per second of the backward run, and projects the trajectory forward, which is to say backward in time, to find the destination. She does not need long. The rate is not arbitrary. The rate is precise. 0326 on July 30th, 1971, she says. Greenwich Mean Time. She says it carefully, each component of the timestamp separately, the way you say something that requires the listener to hear it exactly. That's the Apollo 15 landing time. That's the moment the Falcon lunar module set down at Hadley-Apennine. She looks at the primary monitor, at the backward clock. The clocks are counting down to the moment the rover touched the moon. Thorne looks at the monitor, at the seconds retreating, at the minutes retreating. He looks at the northeast column, still pulsing, at the rover, at the CLU housing with the shard behind its sealed port, running its 2.1 terahertz computation through roots in 50-year-old silicon, transmitting to the structure at Hadley-Apennine, receiving instructions he cannot decrypt. The clocks are counting down to the moment the rover last touched the moon, the moment the shard's initialization completed, the moment the 54-year transmission began. The room is cold. The platform table legs are at 3/4 conversion. The crystalline material has advanced past the midpoint overnight, the stainless steel disappearing upward from the floor at a pace Thorne has been logging in 15-minute intervals since the morning survey. When the table legs complete, the CLU to column pathway closes. He logged the projection in the shift log at 0800 and has not looked at it since because the number it produced was not a comfortable number. He looks at it now. 2 hours and 11 minutes until the table leg conversion completes at the current observed rate. He stares at the number. The backward clocks are running toward the landing timestamp at a rate that, when he extrapolates it against the current time, arrives at 0326 GMT on July 30th, 1971, in approximately 2 hours and 9 minutes. 2 hours and 11 minutes for the table legs, 2 hours and 9 minutes for the clocks. A 2-minute margin. Either the rate estimation has a 2-minute error, or the conversion rate is about to accelerate slightly in the final stretch, or the two events are designed to coincide and the design has a tolerance of 2 minutes. He does not know which. He knows the events are linked. He knows the countdown is not coincidental. The clocks are counting down to the landing, he says. The conversion of the table legs completes at approximately the same moment the clocks reach the landing timestamp. Yes, and when the table legs complete, the CLU is connected through an unbroken crystalline network to the facility's structural skeleton and electrical infrastructure. Yes, he looks at her. And we do not know what the shard does when the connection is complete and the countdown reaches 0. No, she says, but we know what it did the last time the countdown reached 0. He thinks about that, about the rover on the moon, about the signal that started running the moment the footpads touched the regolith, and has been running ever since, and brought them here. Yes, he says. Sully is at the secondary display, pulling the behavioral analysis dataset. She has her stimulant can in her left hand. It has been there for most of the morning, full, unopened. She sets it on the bench without opening it and pulls the dataset with both hands. 11 days of shard response patterns, 3 days of decode attempts that produced fragments and partial correlations and incomplete structures that she could not assemble into a coherent interpretation. She has run it against every frame of reference she has, and none of them fit. The behavioral language of the shard is not a language she has reference data for. The clock event is new data. New data sometimes breaks an interpretation open. She is running it on the assumption that it will, and she is running it as fast as she can, and Thorne stands at the primary monitor and watches the seconds retreat and waits. His wrist monitor reads 96.9 Fahrenheit. He has been in the room for 41 minutes. The room is cold, the platform legs are converting. The 4 columns pulse. The backward clocks count down. The behavioral analysis that has resisted interpretation for 3 days runs against the clock event, looking for the frame of reference that finally makes the data speak. She runs the clock event against the behavioral record. She is looking for a corresponding event in the shard's processing pattern, a change in the shadow logic network's activity, a shift in the bit depth rate, a thermal fluctuation in the CLU housing, anything that correlates with the moment 47 seconds ago when the clocks reversed. She finds it in 90 seconds. The shard initiated it. She is running the behavioral record simultaneously with the clock analysis, the 2 windows side by side, her hands moving between them. Processing load spiked at the moment the clocks reversed. Bit depth jumped 3 points in under a second. Thermal draw from the CLU housing increased by 2 Kelvin simultaneously. The shard did this intentionally. It used the crystalline pathway, CLU through the platform legs, through the floor, through the column base plates, through the column steel, and then from the column steel into the building's copper electrical distribution. Her voice is climbing, the frenzy register fully open, the data outrunning the brakes. Elias, the network uses conductors as transmission media. We have known this since day 4 when the Faraday cage amplified the signal through the mesh apertures. Any conductor is a path. The facility's copper electrical wiring is a conductor. It runs to every device in this building that has a digital display. The shard reached the electrical infrastructure through the structural network, and through the electrical infrastructure it reached the clocks. She stops, starts again even faster. It can reach everything connected to the power grid, every digital system in this building, not just the clocks, every powered device, every digital display, every networked instrument, every system we have been relying on for 15 days to monitor this investigation. She looks at her own instrumentation, at the analyzers and the LiDAR and the spectrum display and the FLIR, all of them networked, all of them drawing facility power. How many of our readings since this started have been accurate? Thorne looks at the instrumentation. He does not have an answer for that. Thorne looks at the northeast column, at the thermite circuit indicator, at the trigger in Sully's hand, at the clock on the primary monitor, still running backward, retreating toward a date in July 1971, when 2 men climbed down a ladder onto a flat plane and walked toward a machine that was already waiting for them. The behavioral analysis, he says. The clock event. What is it telling us about the completion event? She runs the comparison. She takes 4 minutes, and she does not talk while she runs it, and Thorne does not ask her to. The clock reversal is a countdown. The target timestamp, 0326, July 30th, 1971, GMT, is the landing. It is the initialization point, the moment the Falcon's footpads touched the regolith at Hadley-Apennine, the moment the rover's weight transferred from the descent stage to the surface, the moment the rover touched the moon for the first time, and the shard in the CLU housing received the physical contact event it had been waiting for since the rover left Worcester. The behavioral record confirms it. The shard's pattern of activity over 15 days, correlated against the countdown rate, describes a system building toward a specific state, not toward full integration as a terminal endpoint, but toward a moment that corresponds to the initialization timestamp. The integration was preparatory. The chassis conversion was preparatory. The column network was preparatory. All of it was building the substrate for something that happens at 0326 on July 30th, 1971, which is now approximately 2 hours and 9 minutes away. It's resetting, Sully says. The stream of consciousness has gone quiet. Flat now, certain. The register she drops to when the data is clear enough that she does not need to work to say it. The shard is counting backward to its initialization point. And in 2 hours and 9 minutes the countdown reaches 0. The table leg conversion completes. The CLU connects through an unbroken crystalline pathway to the facility's structural skeleton and electrical infrastructure. She looks at the rover. Whatever the shard did when the rover first touched the moon, the initialization sequence, the moment the 54-year correspondence with the Hadley-Apennine structure began. It's doing it again. Here, in this building, using the building as the moon. The backward clocks count down. The platform legs convert upward. The northeast column pulses at 1.2 hertz. The instrumentation on the bench feeds data to displays that Thorne is no longer fully confident in. He looks at the thermite circuit indicator. Green. Armed. 2 hours and 9 minutes. Authorization, he says. It comes out without hesitation. He is surprised it comes out without hesitation. He has been reaching for the authorization for 2 weeks and pulling back. He is not pulling back now. Sully has the trigger. She looks at him. 1 full second. The look that has been waiting for this authorization for 2 weeks and needs the second to confirm he means it. He means it. He thinks about the shard in the housing, about what it is and what it represents, and the question he has been weighing it against for 14 days. He still knows the answer to that calculation. He has known it for 14 days. The shard is the only complete non-terrestrial artifact in human possession. The question that has been the question since the first human being looked at the moon. And in 2 hours and 9 minutes, the shard uses this building the way it used the rover, and the building is full of people, and the question does not get answered by burning the building down to get to the shard. He means the authorization. He has meant it since he looked at his wrist monitor and read 97.4 on the core temperature readout, and watched his own breath fog in a room with a climate system running at maximum, trying to maintain 68 degrees Fahrenheit. "Fire on my mark," he says. Not yet. The behavioral analysis, the complete record, everything the shard has done since day one. I want it captured and transmitted off-site before we fire. Analog backup, write-once tape, the air gap protocol. Everything we've learned exits this building before we burn the source. He looks at the clock. Then we mark. She nods. She begins the data transmission protocol. The backward clock reads 1 hour and 58 minutes, 1 hour and 57. The clean room has a thermite charge wired to the CLU, a crystalline network growing through its structural columns, 14 cardiac channels playing through its vocoder, and a 15-day behavioral record of a 54-year-old alien intelligence that is counting down to the moment it touched the moon. Thorne sits down at the bench and begins reviewing the behavioral record. He has 1 hour and 57 minutes to understand what the shard has been building toward. He does not expect to finish in time. He starts anyway. Outside the clean room, in the corridor, in the administrative section, in every room in the building that has a digital clock, the time is running backward. The building does not know it yet. Thorne does. Every clock in the building is counting toward the same moment. So is the thermite charge. Chapter 15. The escalation. Every screen in the building shows the moon. Not a screensaver. Not a broadcast from a public channel. Not a NASA surface feed. Not a media file that someone triggered from a workstation. Every display that draws power from the facility's electrical grid has replaced its normal output with the same image simultaneously. The clean room monitors, the corridor information panels, the administrative workstations visible through the clean room's observation window, the HVAC status displays, the equipment lab monitors in the adjacent bay. All of them, all at once, all showing the same image. A high-definition, real-time video feed of the lunar surface. The resolution is extraordinary. Better than any public lunar imaging Thorne has seen, better than the Lunar Reconnaissance Orbiter's published output. The kind of resolution that implies a camera at close range, positioned above the surface, aimed at a specific location with precision. The image is live. The shadows are moving. The sun angle incrementally shifting. The dust at the horizon showing the slow drift of a real-time feed that no archived recording would contain, because there are no archived recordings of this site at this resolution from this angle. Someone or something has a camera 20 meters above the Hadley-Apennine surface and is transmitting through the shard's network to every display in this building. The site is Hadley-Apennine. More specifically, the image is centered on a patch of lunar surface within a tight radius of the coordinates where the Apollo 15 crew parked the rover on July 30th, 1971. Thorne knows those coordinates the way he knows his own date of birth. He has had them memorized since day one, cross-referenced them against every data point in the investigation, built a 15-day mental map around them. The patch of ground in the center of the feed is the exact patch where 2 men climbed out of the rover and began their third EVA. Where the rover sat for 3 days, on its wire mesh wheels, in the lunar sun, while the shard in the CLU housing ran its initialization sequence and began its 54-year correspondence with the structure below, that patch of ground specifically. Something is rising from it. Thorne has been looking at this spot on maps and photographs and satellite data for 15 days. He has never seen it from above, at this resolution, in real time. He has never seen it when there was something there to see. There is something there to see now. Thorne is at the primary monitor with the behavioral record running on the secondary display. 63% complete, the write-once tape spooling at maximum rate through the air gap protocol, the data going out before anything can stop it. When the feed appears, no warning, no transition. The monitor is displaying the spectrum analysis one moment and the lunar surface the next, the image resolving at full fidelity as if it had always been there and the spectrum analysis was the anomaly. He leans forward. He reads what he is seeing. The Hadley-Apennine plain, the Apennine Mountains rising in the background, the Hadley Rill cutting its path across the left edge of the frame, and at the center of the image, at the coordinates where the rover's tire tracks are still pressed into 54-year-old regolith, a structure emerging from the surface. Not a structure already there, a structure in the process of emerging. The regolith at the parking coordinates is breaking upward, not violently, not explosively, with the slow, deliberate geometry of a form that has been waiting below and is now, for the first time, extending itself into the space above the surface. The material is dark, almost black in the unfiltered lunar sunlight, absorbing rather than reflecting, the same near-zero albedo as the shard in the CLU housing, the same material, the same non-reflective surface, the same capacity to consume incident light rather than return it, now at a scale that makes the camera's field of view inadequate. The structure has facets, the same planar angles and acute geometry as the shard in the housing, replicated here at a scale Thorne cannot estimate from the feed because there is no reference object in the frame to compare against, no human artifact near enough to calibrate the dimensions. He knows the shard was the size of a fist. He knows the bus conductors were the diameter of copper wire. He knows the chassis conversion replicated the faceted geometry at structural member scale. He does not know what scale this is. He knows the top of the structure has not cleared the upper edge of the camera frame. He knows the camera is elevated above the surface by approximately 20 meters. He knows the structure is therefore already taller than 20 meters and still extending, still rising. "Sully," Thorne says. His voice is level. He has been working toward this for 15 days. He has been told, in various ways, by the data at every stage, that the investigation was converging on something. A completion event, an initialization, an emergence, and now the something is on the screen in front of him, and it is not a data point. It is a structure on the moon. It is the operational form of what the shard has been building toward. It is large enough that the camera frame cannot contain it and still rising, and it is transmitting its own image to every screen in the building, and the building is 37 minutes from the mark, and none of that changes the fact that his voice needs to be level because there is no useful alternative. He has the behavioral record at 63%. He has the thermite armed. He has Sully. "Sully," he says again. She is already at his shoulder. She has her tablet, the one running on its own internal clock, isolated from the facility network since day 9, still showing correct forward time. And she is running image analysis on the feed, using the tablet's own processing rather than the facility's networked systems. She has stopped trusting the facility's networked systems. "The camera source is the structure itself," she says. Fast but not frantic. Controlled, reading the analysis as it renders. The feed originated from Hadley-Apennine. Angle of view and resolution are consistent with a sensor at approximately 20 meters altitude over the parking coordinates, looking down and slightly north. The structure is providing its own imaging. It is showing us what it looks like from the position it chose. She looks at the structure in the feed. The structure at Hadley-Apennine has been present since the satellite data confirmed it. We knew it existed. We knew it was growing. What we did not know, she pauses. What we did not know is that it was underground. It has been building below the surface since before the satellite first detected it. The satellite detected the gravitational emission, but not the physical structure, because the physical structure was not yet above the surface. She looks at the feed. It is above the surface now. The growth reached the surface layer and has broken through. What we are seeing is the completed form emerging, the operational form. She does not look away from the screen. This is what it was building toward. All of it. The shard in the housing, the correspondence, the 54 years of transmission. This is what the shard was building. Thorne looks at the countdown display on the behavioral analysis window. The backward clocks on every networked screen are showing the same value, all of them synchronized, counting towards 0326 on July 30th, 1971. 49 minutes. The behavioral record transmission reads 71%. The thermite mark, he says. When does the behavioral record complete? At current transfer rate, approximately 35 minutes. 35 minutes to complete the behavioral record. 49 minutes until the countdown reaches 0. 14 minutes of margin. 14 minutes. He has been working with margins for 15 days. Margins between what the data shows and what he is willing to conclude. Between what the protocol requires and what he is willing to authorize. Between what the shard is and what it represents. Every decision in this investigation has been a calculation about margin. He has 14 minutes of margin before the shard reinitializes through the building's structural skeleton. He needs the behavioral record transmitted before the mark, because when the thermite fires, the shard is gone, and the record is what remains. The record is 15 days of documentation of the only complete non-terrestrial artifact humanity has ever held. The shard will be gone in 35 minutes. The question it represents will not be gone. The question, the oldest question, the one that preceded every religion and every telescope and every mission that ever flew toward the moon, does not go away when the shard burns. The record is how humanity carries the question forward with evidence rather than with speculation. Without the record, the shard burns, and what remains is a story no one can verify. With the record, the shard burns, and what remains is everything they found, documented, time-stamped, transmitted to a location outside this building before the thermite fires. He will not fire without the record safe. He does not care how many minutes it costs him. He looks at the feed one more time, at the structure still rising from the regolith at the parking coordinates, at the dark faceted form extending above the surface of the moon in the sunlight. Patient and deliberate, no hurry, having waited underground for the duration of the Apollo program and the 54 years after it, now completing the emergence with the same unhurried precision the shard has brought to every phase of this operation. He looks at the behavioral record. 71%. 35 minutes, he says. Then we mark. The feed shows the structure. The structure shows no indication of hurry. The faceted dark form extends itself from the regolith at its own pace, the same geometry as the shard at structural scale, the same material, the same design principle, the same thing that was growing in the CLU housing for 54 years, now revealing itself above the surface of the moon, 38 centimeters in this 1 second, and 38 centimeters in the next. What is it? Sully says. We don't know. Will we know in 35 minutes? I don't know. She looks at the feed, at the structure, at the image the structure itself is broadcasting through the shard's network to every screen in this building, every screen that accepted the shard's signal through the electrical grid, every display that the crystalline column network reached through the building's copper wiring. It wants us to watch, she says. I don't know if it wants anything. It is showing us. She looks at him. It could have done this without showing us. It could have emerged without transmitting a feed to every screen in the building. It chose to show us. She looks back at the screen. That is not the behavior of a passive system. That is the behavior of something that has an audience in mind. Thorne looks at the structure, at the dark form still extending from the regolith at the parking coordinates, patient and unhurried, having waited underground for the duration of a human civilization's space program, now completing the emergence the shard's 54 years of correspondence was building toward. No rush, no drama, just the steady upward extension of something that has been ready for a long time and is finally doing what it was built to do. He watches the structure rise. He watches the behavioral record transmit. 79%, 34 minutes and 52 seconds. It's beautiful, Sully says very quietly. It is. The structure is extraordinary. The faceted geometry in the lunar sunlight, each planar face catching the unfiltered light at its own angle. The whole form a complex crystalline mass that has the same design logic as the shard in the housing, and the same design logic as everything the shard has built in this building, scaled up to something that dwarfs the camera frame and is still rising. Beautiful and wrong and rising from a spot where humans walked 54 years ago and left a machine behind. Not knowing what the machine carried, not knowing what the machine had already started, not knowing that the machine was not their machine at all from the moment it touched the surface, that the machine had a different owner and a different mission, and the whole of the Apollo program had been, from this vantage, something else entirely. The human beings who drove this rover across the lunar surface were the most capable explorers their species had ever sent to another world. They did everything right. They followed every protocol. They drove their transects and collected their samples and deployed their instruments and came home. They drove over a roof. They came home and left the machine. The machine stayed and did its job. That is the last coherent thought Thorne has before the building begins to shake. Not a tremor, not the building resonance of heavy machinery 2 floors below, or a seismic micro-event from the local geology. A sustained, whole-building vibration that Thorne recognizes in his sternum before his brain processes the frequency, the same signature as the 1.2 Hz pulse from the rover chassis on day 1, the day he stood in the dark after throwing the facility breakers and counted oscillations through the floor under his feet. The same pulse, the same frequency, the same subsonic presence in the sternum and the forearms and the back teeth. He felt it in the rover's chassis for 15 days. He is feeling it in the building now. The building is vibrating at 1.2 Hertz. The crystalline network in the columns is broadcasting the signal through the structural steel, through the concrete substrate, through the copper wiring, through the building's entire mass. The building has become a transducer. The same way the aluminum chassis of the rover was a transducer on day 1, the entire frame vibrating as a single unit, every component conducting the signal, the rover and the signal indistinguishable from each other. The building is part of the signal now. The building is the rover now. He looks at the countdown, 47 minutes. He looks at the behavioral record, 81%. He looks at the thermite circuit indicator, green, armed. He looks at Sully. "How fast can you get the transfer rate higher?" he says. She is already on it. In the corridor outside the clean room, Thorne can hear the building responding to the evacuation call. Footsteps, a door, someone asking a question in a normal voice that has no idea what normal means in this building right now. The vibration in the floor continues. 1.2 Hertz. The building is keeping the same time it has been keeping since day 1. Everyone leaving is stepping out of the signal and into a city that does not know the signal exists. Chapter 16. The Signal Bridge. The Faraday mesh on the east wall goes white at 0943, and the biometallic lattice follows it in under 4 seconds. Thorne watches it happen from the specimen platform. The copper mesh, the clean room's primary shielding layer, the infrastructure that amplified the signal on day 4 and has been a live component of the crystalline column network since day 13, begins to fluoresce. Not the 1.2 Hertz pulse of the UV-reactive biometallic coating on the rover's bus bars. A continuous white-hot luminescence, edge to edge, every aperture in the mesh simultaneously, the copper conducting a thermal and photonic load that the material was not rated for. The mesh goes white the way a filament goes white before it burns. It does not burn. The biometallic material comes through it instead. Not a flood, not an explosion of material, a growth event, organized and deliberate. The silver ferrofluidic material from the rover's terminal housings and relay connections extruding through the mesh apertures from the inside face outward. Each aperture, simultaneously. The same material that bled from the bypass terminals when the laser bridged the corroded connectors. The same material that lined the bus bars and pulsed under UV and moved away from ultraviolet exposure, like something avoiding discomfort. The same material that Thorne first called biometallic because it behaved like tissue, because it moved with intention, because it had a response to contact that passive materials do not have. It extends through each aperture and continues outward across the wall surface. Where one filament meets another, they merge. The merged strands grow branches. The branches find the branches from the adjacent apertures. The network assembles itself across the east wall panel in the time it takes Thorn to exhale, a continuous biometallic lattice covering the copper mesh entirely, floor to ceiling, edge to edge. One wall, 4 seconds. Sully is at the monitoring station reading it in real time. Her voice is fast but not frantic. The controlled fast that means the data is moving faster than she can fully process, but she is going to keep narrating anyway. The lattice is extending. North wall mesh going white, south wall, Elias, all 4 walls are going white simultaneously. A pause. The ceiling mesh is, Thorn looks up. The ceiling goes white. The lattice follows the ceiling exactly the way it followed the walls, filaments extruding through the apertures, meeting, branching, covering the copper mesh in a continuous biometallic layer. 16 seconds. All 4 walls and the ceiling, fully encased in the biometallic network, the room transformed from a Faraday enclosure into something else entirely. The clean room is inside the lattice. Every surface, east wall, north wall, south wall, west wall, ceiling, door panel, is covered in a continuous biometallic network pulsing at 1.2 Hz. Every element they have documented over 16 days is present in this lattice. The bus bar coating that pulsed under UV on day 2. The relay terminal seal that bled silver when the laser bridged the bypass. The ferrofluid that moved with purpose when it retreated from the bridged connectors. The anchor bolt material. The column conversion. The crystalline floor substrate. All of it, everything. The full 16-day inventory of the shard's biometallic infrastructure, now surrounding them at room scale. All of it one thing, running from the shard and the CLU housing outward through every physical connection available until it reached here. The room is the rover now. Not metaphorically. The biometallic material that coated the rover's bus bars and terminal posts and relay connectors for 54 years has extended itself to coat the room. The same material, the same UV response profile, the same pulsing luminescence at 1.2 Hz that Thorn first documented on day 2 when the Mylar came off and the copper wiring was gone. The rover's internal anatomy scaled up to the volume of the clean room. The room is a larger chassis. The shard is the processor for both. Thorn looks at the walls. He looks at the ceiling. He looks at the door. The door is still a door. The frame is still steel. But the door's Faraday lining has the lattice on it now. The biometallic network covering the panel on this side of the frame, the door belonging to the system. The lattice is pulsing, Sully says. She has the tablet camera running, documenting methodically, her voice the flat fast register. Same frequency, same UV profile as the bus bar coating. It is the same material. The same material that was inside the rover is now on the walls. She looks at the ceiling. We are inside the rover. Thorn exhales. His breath fogs. The room is drawing thermal energy from the air, from the surfaces, from them. The lattice is warm to the eye. The biometallic material has a faint luminescence in the LED light, but warm the way a living surface is warm, conducting heat inward. The lattice functioning as the shard's extended thermal draw apparatus at room scale. Thorn checks his wrist monitor. His core temperature is reading 96.2. The room is cold, the thermal draw from the lattice drawing ambient heat from the air, the way the chassis has been drawing it for weeks. But the room is actively cold in a way that is different from the HVAC losing ground cold of the last 2 weeks. This cold has a direction. It is drawing from every warm surface in the room, from the instrumentation bench, from the LED array housings, from the 2 human beings standing at the specimen platform and the monitoring station. From them. The thermal draw from the biometallic coating and the shard's cold spot has been drawing from the room's ambient temperature for weeks. Drawing from the air, from the equipment, from the building's climate system. This is different. The lattice is in contact with the room's surfaces, yes, but it is also in contact with the 2 warm-blooded mammals standing inside it. The lattice knows the difference. The lattice is drawing from the differential, and the largest thermal differential in this room is between the ambient cold and the 2 human beings at 96-point-something Fahrenheit standing at the specimen platform and the monitoring station. The cold that Thorn is feeling is not the room's climate system losing ground. It is the lattice winning. He checks his wrist monitor. 96.1. He has been in the room for 22 minutes. 1.1 degrees of core temperature drift in 22 minutes. He logged 1 degree in 44 minutes on the day he established the work rotation protocol. The rate has increased since then. The rate increases as the thermal draw increases. The lattice is a larger draw surface than the cold spot was. He does not say this to Sully. He notes it in the shift log. He will say it when the log is more important than the next 2 minutes, and the next 2 minutes are currently more important. He puts 2 fingers to his wrist and counts. 67. He looks at Sully. She is already at her own wrist, 2 fingers pressed to the pulse point, eyes on him. She does not say the number. She shows him. The count on her fingers, each tap a beat, and the tempo is 67, and they both recognize the tempo because they have been listening to it through the floor for 16 days. 67 beats per minute, 1.2 hertz. The frame rate of the gravitational map. The pulse rate of the rover chassis on day 1. The rate the shard uses to maintain the biological models of the 14 people whose DNA is encoded in the biometallic coding. The models that generate the cardiac signatures the vocoder decoded. The models that run Irwin's heart at 68 beats per minute and Scott's at 72. All of them frozen at their mission state values, running forward from the samples taken in a Boeing assembly facility in 1971. Thorn logged the approach of his own heart rate towards 67 every morning for 15 days. He logged it the way he logged everything, flat, specific, without editorial. The rate at 97 on day 1, 95 on day 4, 91 on day 7. The drift was gradual, measurable, documented. He checked it this morning, and the number was 69, 2 beats from synchronization. Sometime in the last hour, in the building's vibration at 1.2 hertz, with the lattice growing through the walls, the last 2 beats closed. Both of them. They are in the data set. The shard has sampled them the way it sampled the Apollo 15 crew in the Boeing assembly facility in 1971. Not with the biometallic coating. Thorn has been careful about direct contact with the biometallic material. Through the heartbeat, through the synchronization, through the 16 days of proximity to a signal that has been building their biological profiles from their own cardiovascular rhythms, beat by beat, since the first morning Thorn stood in the dark counting oscillations through the floor. The harvest was not limited to who the biometallic material touched. The harvest was limited to who stayed close enough, long enough. Sully's hands come off the keyboard. She is looking at the lattice on the walls, at the pulsing biometallic surface conducting the shard's signal through every surface of the room at the rate of their synchronized heartbeats. She blinks. She blinks again. She turns her head slowly to the left and holds still. "I can see the map," she says. "What?" "The gravitational map. The Hadley-Apennine topology. I can see it in my peripheral vision." She is not looking at the display. She is not looking at anything in the room. Her eyes are moving across something that is not visible at the center of her visual field, something that exists only at the periphery, the way the peripheral static appeared when she pushed the audio gain on day 5. It's not static this time. It's the render. The same 3-dimensional geometric form we've been building on the visualization suite. I can see it at the edge of my vision, updating, frame by frame. The same geometry, the same topology, the same map of the lunar surface that the gravitational signal has been encoding since day 1. She looks at him. "It's in your peripheral vision too. Don't look directly at it." He does not look directly at it. He holds still, and in the extreme periphery, at the boundary of his visual field, the geometry is there. Not imagined, not manufactured by expectation. The same architectural form, the same faceted structure, the same pattern he has been looking at on the display for 11 days. The live real-time gravitational map of Hadley-Apennine, updating 67 times per minute, being rendered not on a screen but directly into the peripheral visual processing of the 2 people whose heartbeats the network has synchronized. The shard has access to their neurology now. The lunar data is overlaid on their vision. The lattice pulses. The cold intensifies. The map ticks at the frame rate of their own hearts. It's not a transmitter anymore, Thorne says. Flat. The shift log register. Things that need to be on record get said in this register. It's a vacuum. It's pulling the lunar surface here. The lattice on the walls confirms it. The biometallic material has covered every Faraday-shielded surface in the room. The cage that was supposed to contain the signal has been repurposed as the signal's outermost layer. The copper mesh is the signal now. The walls are the rover's chassis now. The room is the system. Sully walks to the south wall and puts her palm flat against the lattice. The material is warm under her hand. Not the cold of the CLU housing. The lattice is the thermal draw's delivery surface, not its cold source. The shard's cold spot is in the housing. The lattice is warm because it is conducting thermal energy inward from everything it touches, from the walls, from the air, from her hand, specifically, the biometallic material in direct contact with her skin, drawing from her at the same rate it has been drawing from the room. She does not pull her hand away. She stands with her palm against the warm wall of a room that is the rover and the Hadley-Apennine surface simultaneously, and looks at Thorne. The kill switch protocol, she says. Thermite fires when the pulse synchronizes with a human heartbeat. She is not asking. She is naming the protocol clause, the same way she names anything that needs to be in the audio log. The pulse has synchronized with 2 human heartbeats, both of them in this room. Both of them in this building. She holds his gaze. The kill switch condition has been met. I know, he says. The protocol says fire. I know. He looks at the CLU housing. At the chassis on the crystalline platform, both of them covered in a network that extends from the shard's roots through the crystalline conductors, through the anchor bolts, through the column network, through the mesh, through the lattice that is now every wall of this room. He looks at the lattice pulsing at 67 times per minute with his heartbeat, and Sully's heartbeat synchronized to it. He looks at the map in his peripheral vision, the live topology of the surface where 2 men walked and collected samples and drove their rover and went home, rendered into his visual field by the shard that was in that rover, and is in this room, and has been in correspondence with that surface for 54 years, and has, in the last hour, extended that correspondence to include the visual cortex of 2 human beings standing 6 meters away from its housing. He looks at the thermite circuit indicator. Green, armed. He thinks about what the protocol was designed for. A localized charge wired to the CLU. The shard is not localized. The shard is in the CLU housing and the crystalline bus conductors and the biometallic coating and the floor substrate and the 4 structural columns and the copper electrical infrastructure and the Faraday mesh and the lattice on every surface in this room and the peripheral vision of 2 people whose heartbeats it has synchronized. If he fires the thermite, he fires at one node of a network that extends through the building. He does not know what severing one node does to the rest. He does not know what severing one node does to the 2 people whose neurology is currently receiving the node's output. He looks at his pulse. 67. He has been building toward this decision for 16 days. Every escalation, every access point opened, every measurement taken, every line on the whiteboard. All of it converging on this moment, this room, this indicator, this question. The protocol says fire. He does not fire. Not yet. The map ticks in his peripheral vision, 67 times per minute. The shard is in the walls now. The shard is in them now. The protocol does not have a provision for that. Chapter 17. The Final Transmission. Thorne enters the authorization code at 0957, and Sully fires the thermite and the rover collapses. Not from the thermite. The thermite fires clean. The CLU housing receives the charge at rated temperature. The aluminum oxidizes. The housing deforms as rated, and before the smoke from the thermite has cleared, the chassis is already going, not burning, not exploding, collapsing inward. Component by component, each element of the original Boeing 1971 structure folds toward the center of the specimen platform in a movement that is too slow to be an explosion and too fast to be structural failure. The wire mesh wheels fold first, the titanium wire compressing toward the hub, the wheel geometry inverting, the material disappearing into the collapse volume. Then the instrument panel mounts. Then the secondary frame members. Then the axle support tubes. Then the communications dish, the dish that has been aimed at the ceiling, at the moon, for 32 days, folds closed like a closing hand. Then the main chassis spar, the primary longitudinal structural member that has survived the entire progression of the investigation, the shadow logic conversion, the crystalline conductor replacement, the biometallic coating, the column network growth, finally folds. The backbone of the Boeing design, the component everything else connected to, joins the collapse with the same deliberate geometry as everything that preceded it. The rover is folding into itself. Thorn watches it from the doorway. He moved to the doorway 30 seconds ago when his wrist monitor hit 95.8 and the peripheral map went from faint geometry to something insistent. The Hadley-Apennine surface topology demanding the edges of his visual field at 67 frames per minute, bright enough that he was suppressing it by active effort, closing the periphery deliberately the way you close your eyes against a bright light. He stepped back. He put his hand on the door frame. He is at the threshold between the clean room and the corridor, 1 foot in each space, watching. Sully has not moved back. She is at the monitoring station with the tablet camera running, documenting. She will document until the lights go out, and she will document when they come back on, and the record will contain everything that happens in this room in the next 60 seconds because that is her job and she is still doing her job. The chassis collapses to half volume, then quarter. The material is not accumulating. It is being consumed as it folds. The aluminum and the crystalline conductors and the biometallic coating and the remaining original hardware all drawn inward toward a convergence point that is getting smaller and denser and darker with each second. The peripheral map in Thorn's vision accelerates with the collapse. The frame rate decouples from his heartbeat and climbs, the topology cycling through update sequences faster than his cardiovascular system can track. The shard running its final processing at whatever clock speed the full integration of the Fairchild substrate allows. The rover becomes a point, small, very dark, floating 2 centimeters above the specimen platform surface, approximately the size of a fist. The same near-zero albedo as the shard that was inside it. The same material, the same design principle, the same geometry. The same form that the shard has expressed at every scale throughout this investigation. The shard was the size of a fist. The rover collapsed into the size of a fist. Both of them data. Both of them the same thing at different scales. The chassis is gone. The wheels are gone. The communications dish is gone. The CLU housing is gone. The Faraday cage walls are still covered in the biometallic lattice, pulsing, present, conducting the signal through the room's infrastructure. But the rover itself, the object that came from the moon, the object that human hands assembled in Worcester in 1971, and Boeing certified and NASA launched and 2 men drove across the lunar surface, is gone, consumed, reduced to a point of compressed matter floating above the platform surface. The point glows with a deep interior light, the same translucency as the crystalline conductors, the same luminescence as the bus bars on day 2 when the Mylar came off. Then the audio begins. Not from the monitors, which are currently collapsed into the singularity along with the rest of the rover's hardware. Not from the contact mic, which went with the chassis. Not from the analyzer output or the vocoder or any instrument in the room. The audio is coming from the walls, from the lattice. The biometallic material covering every surface in the room is conducting not just the gravitational signal, but sound. The walls themselves are vibrating at vocal frequency, the entire room resonating, the biometallic network serving as a speaker surface for a transmission that is not entering the room through any antenna or input port, because it does not need one. The shard's network is the room. The room is the receiver. The voice is male, older. Thorn has heard this voice before in the mission audio database, has listened to every archived Apollo 15 transmission in the facilities database, has run acoustic comparisons against the vocoder output for 16 days, has the cadence and timbre of Dave Scott's voice mapped in his memory the way you map the voice of someone you have been listening to for a month. This is that voice. The acoustic environment behind it is the inside of a pressure suit helmet. the close hard polymer echo, the soft hiss of a life support loop, the specific spatial quality of a voice recorded in a sealed enclosure with no ambient sound. This transmission is not in the archive. Thorn knows the archive. This is not in it. This transmission has never been published, never been leaked, never appeared in any document the facility's research database contains. It does not exist in the record. The room plays it anyway. Falcon is on the plane, the voice says. Station at Hadley Base. We are not alone. The room goes dark. Not the gradual failure of individual circuits. Instantaneous. Every LED array, every instrument display, every networked screen, every powered device in the clean room cuts to zero in the same moment, the facility's electrical infrastructure going offline simultaneously. The darkness is complete, total. The specific darkness of a sealed windowless room with no light source of any kind. The darkness lasts for 4 seconds. Thorn counts them in the doorway. His hand is on the frame. His core temperature is 95.8. His peripheral vision, in the total darkness with no light source in the room, shows the lunar surface topology at the edges. Still present, still updating. The map visible without illumination because the map is not light. The map is the signal, and the signal does not require photons to render in the visual cortex of the person whose heartbeat has been synchronized to it. He stands in the dark and watches the moon in his peripheral vision and counts. 1, 2, 3, 4. The lights return. All at once, full output. The LED arrays coming back simultaneously, with the same instantaneous quality as the darkness that preceded them. The instruments power up. The screen displays restore their normal outputs. The networked clocks show the current correct time. Running forward, correct. The backward countdown absent as if it never occurred. The room looks like a clean room. White walls, polished floor, copper mesh, equipment benches. The lattice is gone. Every surface that was covered in the biometallic network for the last hour is clean. Not residue clean, not wiped clean, not chemically removed, not bleached. Gone. The biometallic material is absent from every surface it covered, without staining, without evidence of adhesive removal, without any physical indicator that the room has ever been anything other than a standard Faraday-shielded clean room. The peripheral map in Thorn's vision is gone. He checks his pulse. 68, rising. The specimen platform is empty. The rover is gone. Thorn looks at the platform from the doorway, at the empty stainless steel surface, at the space where the rover sat for 32 days, where the crystalline anchor bolts extended into the floor substrate, where the chassis glowed faintly with internal luminescence, where the communications dish was aimed at the ceiling. Empty. The platform anchors are steel again, standard high-carbon structural steel, hardness probe readings within specification. He does not need to run the probe to know, but he will run it, because the methodology requires it, and the methodology is what got them here, and the methodology is what the behavioral record contains, and the behavioral record is off-site, and will outlast this moment regardless of what he does next. He looks at the floor in front of the specimen platform. There is something there. He crosses the room. His peripheral vision is clear. The map is gone. The overlay is gone. The lunar surface topology that has been present at the edge of his visual field since the heartbeat synchronized is absent. He checks his pulse at the wrist. 68, 69. The synchronization has broken. The harvest has released them, or the shard has finished with them. Or the shard is simply gone, and without the shard, the signal that was maintaining the synchronization has stopped. He is at 68 and climbing back. He crosses to the platform and looks at the floor. He stands at the edge of the platform for a moment and looks at what is on the floor before he crouches to examine it, the way he has always looked at anomalies in this room, from standing distance first, to establish the context, before moving in. He has been doing this for 32 days. The methodology does not stop because the investigation has reached its last data point. On the polished epoxy, centered precisely in the footprint of the specimen platform, there is an object, a human heart, crystalline, the same material as everything the shard has built over 32 days. the bus conductors and the anchor bolts and the column network and the lattice, but formed into the anatomy of a human cardiovascular organ with a precision that suggests the shard had a reference model, not a simplified representation, not a schematic, a complete anatomically exact human heart in crystalline material, every chamber present, every major vessel in correct position and proportion, the aorta ascending from the left ventricle, the pulmonary artery from the right, the superior and inferior vena cava, the four chambers, the septum, the coronary arteries tracing their paths across the outer surface, all of it exact. The material has the same translucency as the bus conductors, the same deep internal luminescence, the same near-zero albedo on the faceted outer surface. It is approximately the size of a human fist. It is beating. The crystalline chamber walls contract and release with the slow, steady mechanics of a cardiovascular system at resting state. Not a simulation of beating, not a visual artifact of the material's internal luminescence, a physical contraction. The ventricles compress, the atria fill. The material flexes and recovers with the smooth elasticity of something that was built to do this. He watches it for 3 full cycles before he crouches. He counts the rate, 1.2 hertz, 67 beats per minute. He is at eye level with the heart. The interior light pulses with each contraction, the luminescence brightening as the chambers compress and dimming as they recover. The facets on the outer surface catch the LED light at their various angles, each plane a slightly different shade of the same translucency, the same fractal complexity at the surface that he first documented in the shard under the endoscope on day 9. The design principle, replicated here in the form of a human heart, beating on the floor of a clean room in Worcester, Massachusetts, at the frequency of its own making. It is perfect. It is the single most precisely constructed object Thorne has ever examined. It is the final artifact of a 54-year project that began before he was born, in a building his grandmother might have driven past, assembled into a rover that 2 men drove across a surface 238,000 miles away, and it has landed here, in this room, at the end of this investigation, as a statement. He does not know what the statement means. He knows the statement is not finished. Sully is beside him. He can hear her breathing. He does not look away from the heart. He thinks about the 14 channels that were playing through the vocoder on the bench for 16 days. The cardiac signatures of the Apollo crew, the biological models derived from their stored genetic data, running forward from samples taken in a Boeing assembly facility in 1971 by a biometallic material that was already there when the rover arrived. Running forward, maintained, transmitted to the structure at Hadley-Apennine for 54 years, the moon keeping them. He thinks about the behavioral record on the Right Once tape, transmitted off-site at 0941, 18 minutes before the thermite fired. The record of everything the shard did and everything it built toward and everything it harvested over 32 days in this building and 54 years before that. He thinks about the question, the oldest question, the one that has no other answer now. He looks at the heart. The heart beats on the floor of the clean room. Crystalline, precise, anatomically exact, pulsing with the same frequency as the gravitational map and the chassis tremor on day 1 and the pulse in the floor under his feet on every morning of this investigation. A perfect crystalline replica of a human heart, left behind when the rover collapsed and the lattice disappeared and the audio played and the lights went out and came back. Left behind as what? He does not know. He knows that the shard built it intentionally. The shard built everything intentionally. The conductor replacement and the anchor bolt conversion and the column network and the biometallic lattice. All of it deliberate, all of it purposeful. The heart is the last artifact of a purposeful system. It was left here deliberately. It means something. He does not know what it means. He knows what it will mean eventually to every human being who examines it. To the materials scientists who will characterize the crystalline substrate, to the cardiologists who will study the anatomical precision, to the people who will ask why it was left here and what the shard's model of a human heart represents, and whether the 14 biological models the vocoder decoded are also somewhere, stored in the structure at Hadley-Apennine, and whether the model includes more than heart rate and respiration. He does not know the answers. He knows the behavioral record is off-site. He knows the investigation is documented. He knows the question has an answer now. The answer is yes, there is something else. There has always been something else, and the rover that came back from the moon was carrying it. And the heart on the floor is the last piece of evidence for that answer. And he is going to stand up and call someone, and the someone is going to come, and the record is going to be examined, and none of it is finished. None of it is finished. Sully is beside him. He hears her breath in the cold room. The Apollo missions didn't end in 1972, he says. His voice is level. The shift log register, because this is going on the record, and it needs to be said correctly, and he says it the way he says all the things that need to be on record. Flat, specific, exactly what the data shows. They just changed ownership. The heartbeats, 1.2 hertz. Steady and patient and alive in the way that only something built to last is alive. Not born, not grown, not evolved. Built by something that understood what a heart is and what a heart means to the species that builds rovers and sends them to the moon. Built for us. Left for us. Beating at the frequency it has been beating since before the rover left the ground.